Max flow and min cut problems. So let me first define what is a fault tolerant oracle. So in the fault tolerant oracle problem, what we do is we are given a graph and we do some pre-processing of the graph to compute some data structure, which we say as oracle. So this data structure is just storing some information about the graph, and after that some queries come, and all queries are of the form that they contain a filling set, and they may contain some uh, additional information, like additional information also. And what we have to output is some property of the graph g minus f. So if it is say fault tolerant distance oracle problem, then the query will be the pair of vertices and the filling set, and we'll have to output st distance in g minus f. Now in this talk we are looking at flows and cuts problem. Okay, so yeah, one thing, like in general, like for the oracle problem, the goal is to obtain a data structure which has efficient query time and compact space. So why we want efficient query time and compact space is because, like one solution could be like you can store all the all possible, you can store answers to all possible filling sets, but this is quite inefficient. So we want ideally a query time which is better than recomputation from scratch, and space should be ideally polynomial in the size of the graph. It should be independent of number of failures we have. Okay, so in this talk we'll be looking at the problem of flows and cuts. So our input will be a directed graph with a source S, a sink T, and a bound K on the maximum number of failures that we have in the graph. And we have to design data structures such that for any query set f of at most k failing edges, we are able to output st max flow and st min cut in the graph g minus f. So basically we are looking at two oracle problems. One is for flows, one is for cuts. Um, since our source and sink is already fixed, our query is just consisting of a failing set of k edges, and we have to output st max flow in g minus f. And for min cut, again our query is set f of failing edges, and we have to output an st min cut in g minus f. So any questions till now? Okay, so here is an example. So suppose you have this graph, then you can see that the size of the max flow and the min cut is 2 in this graph. Now suppose you fill this edge. Then can anyone tell what is the value of new min cut after failure of ex? Right, so the min cut will become 1, and um, if you look at any original cuts in the graph that is containing the edge ex, then those original cuts will again be, the original min cuts will again be min cuts in the new graph. And if you have to update the flow, then you have to just cancel a flow along an S to T path containing the edge ex. Now if the edge ey fails, then the st min cut size remains same, but also the original min cuts of the graph will still be the min cuts in the new graph. And if you have to update the max flow, then you might require rerouting flow through edge ey if if the initial flow that you have is such that f of ey is 1.
Do you want the actual cut in the flow or just the values?
So like we look at all three versions, like we just want to know the value of the flow, the exact flow, and the exact partitioning of the min cut. Okay, so here are some known results for this problem in a directed setting. So for single failure, we can have oracle with a constant query time, and it has just order n space, and it can report the cut in order n time. If we have two failures, then there is an oracle of n square size. It can report the value of the cut in constant time, and it can report the actual cut in linear time. And recently, so these two results are for unweighted setting, that is all edges have unit capacity. Recently there is a result which um, obtains oracle for the weighted setting for single failure. It has n square size and constant query time, and time to report cut is order n. Mm, some other versions that people have studied are all pairs min cut oracle for undirected graphs, Steiner min cuts, global min cuts, and also dynamically maintaining min cuts if the graph is having both edge insertions as well as edge deletions.
So can you understand? So is there a pre-processing time you allow RP to?
Yeah, so we allow pre-processing time. Um, the like we just like in our results the pre-processing time is just polynomial in n, but we do not optimize it.
So just to then understand the last row, so I could just go over all edges, the tables last row,
Okay.
and just remember the cut values and create this table.
So like we can have like we can create a table, but so like this result has like one is that if you want to report the actual cut, then it's non-trivial, because
As in, I can pre-process and store it in the table also.
then the space will increase, it will become n cube,
But the query time,
right? And so I don't remember, like this is like Surendra's paper. So we also have this, I think, order n time. If so, we can also improve the oracle size to order n if you guarantee that you are giving a valid edge, and you are also saying whether it's carrying a flow or not. Is it? Okay. So the only constraint is that it should be a valid edge. Okay, so in this talk, we are just focusing on ST min cut and XT max flow problem in directed graphs, and we are focusing on graphs with unit capacity. And we parameterize our results as a function of lambda. So throughout the talk, we'll use lambda to denote the value of ST max flow in the original graph, or the value of ST min cut in the original graph. So what we show is that for the max flow problem, we can get like if there is just a single and dual failures, then we can get an oracle of lambda in size, and time to update flow is linear in n, and we can also report flow through a certain given edge in constant time. And for general failures, our oracle size is lambda to power k into n, and time to update the flow is order n. Now this first row result is optimal. Like if you allow parallel edges, then we can show that we cannot improve on lambda in size, and but the second result is not optimal. Like if you allow higher update time, then this oracle size can be reduced. So it can be made just a lambda into n. For min cut, we improved the oracle size from n square to lambda into n, where lambda is the size of the ST min cut in the original graph. And for general k failures, our oracle size is lambda to power k into n, and again the time to report the cut and time to report the size of the cuts, these are optimals, order n and order 1. Again we show that the result for 2 failures is optimal, but for k failures, like if you don't worry about reporting time, then we can make, then it's already known that we can make this lambda into n. Now in this, okay, so one more thing, like as a byproduct of this result for reporting the size of the min cut after constant many failures, because we have linear size, if like lambda will be just like you can set lambda to be just k plus 1, and then we can get a ST reachability oracle which has linear size and constant query time. So prior to this, the ST reachability oracles were known for only all pairs setting if we need if we require constant query time, and here we show that we can get it for a fixed S and T order n size. So for rest of the talk, we'll be just focusing on the problem of reporting the cut size for 2 failures and general k failures. And in order to understand these results, we'll also go through ST min cut oracle for single failure. Okay, so the ST min cut oracle for single failure is based upon the structure of SCCs that we get in the residual graph. So suppose this is a directed graph which S is source, T is sink, and there are I've colored the edges into 3 colors. So one are edges in blue color, another is edge in red color, and third is edges in black color. So can anyone see what is the distinction between these 3 categories of edges? So blue edges are simplest. Also, these two and these two are blue edges.
They're part of some min cut.
Right, so these blue edges are part of some ST min cut. So red edge is not part of min cut, but it is going from sink side to source side in a min cut. So if you take this min cut, like first edge here and second edge here, then the red edge is going from sink to source side. So blue edges will be fully saturated under any flow. Red edges will carry zero flow under any flow. Now black edges are not separated by any ST min cut, so they may have flow value 0 or flow value 1. Now so suppose we look at the residual graph and we look at SCCs in the residual graph. So I'll take a simple ST max flow. So SCCs are strongly connected components. So suppose you have suppose this brown path, this one and this one is correspond, like these two paths correspond to ST max flow. Then in the residual graph, like we are just looking at flows with integer values. So each edge is having flow either 0 or 1. Now if we just take a residual graph with respect to this flow, then some edges will change their directions. Precisely the edges that are contained in either the first path or in the second path will change their direction. After this, suppose we look at the SCCs, then how many SCCs will we get? Right, so we'll get 4 SCCs. So this is the first SCC. Because this brown edge has changed the direction, this brown edge has changed the direction, so now this is a cycle, this is a cycle. So this is the first SCC. This is the second SCC because this path is now reversed. Similarly, this is the third SCC and this is the fourth SCC. So we can see that the edges that were separated by min cut, so the blue edges which were part of the min cut are separated by SCCs, and the red edge which was going from sink side to source side under a min cut, this is also separated by SCC. And this is not a like a special case scenario. Like what we can show is that if you look at a residual graph g of f corresponding to any max flow f, then the across the SCCs are either edges that are part of min cut or edges that are going from sink side to source side. So these edges are the edges that cross a cut, and the edges that are within the SCC are the edges that are never crossed by a min cut. So they are never crossing a min cut. Now suppose you want to design ST min cut oracle, then failure of which edges can decrease the min cut size? Right, failure of only blue edge, like because we have a single failure, so only if a blue edge is failing, it can decrease the min cut size. So basically, we want a data structure that can efficiently tell whether an edge is a blue edge or not a blue edge. So what we can do is we can store the SCCs. The edges that are within the SCC are not cut edges, but edges across the SCC can be cut edges. But we have to still distinguish between the edges that are going from source side to sink side in the cut and from sink side to source side in the cut. So this is what we have already seen. Now what, like if you want to distinguish between blue and red edges, then what we can do is we can compute a topological ordering of the SCCs, and all the edges like in the topological ordering, all the edges will be going from left to right, but blue edges will be appearing in the reverse direction, because in the residual graph they are fully saturated, so their direction is from right to left, but the edges that are not carrying flow or that are not part of ST min cut will be appearing in the left to right direction. So just by looking at the direction of the edges, we can tell which edges are part of min cut, which edges are not part of min cut. So basically, like we have like from these SCCs we'll get a DAG. The blue edges were actually in the reverse direction in the residual graph, but when we look at the actual direction of the blue edges, then in the topological ordering they are reversed. Any questions here?
I'm confused about the direction. Is this reverse direction, or is supposed to start with 4?
So first is like in the residual graph, these 4 blue edges will be in the opposite direction,
Okay.
because they are fully saturated. So
But like in the picture below, the first node is supposed to be 4 on 1.
this is 4.
Okay.
So sort of 4 will have 2 outgoing edges in the residual graph.
Right.
Like these 2 will be the outgoing edges. 1 will have 2 incoming edges. These 2 edges will be the incoming edges. So in the residual graph, this is the topological ordering 4, 3, 2, 1.
I think the arrow directions.
The blue ones are the original.
Yeah, so blue ones are the original directions.
Oh, okay. I see. Yeah.
So I had a question. So not a single deletion of a blue edge does not
decrease. It does. Right.
Will the SCCs remain the same irrespective of which maximum you consider?
Right.
They will.
Yeah, because like you can have an alternate characterization that you can define an equivalence relation, and the equivalence relation will be two vertices are related to each other if they are not separated by any ST min cut. Like in the residual graph, W edges will be like this. And if you look at the residual graph edges, then all the edges will be um, from left to right. But when we look at actual direction of the edges, the min cut edges are reversed.
I'm talking about the DAG. Like, you have made a DAG using the SCC,
Right.
right? So the edges are supposed to go from one side to the other.
Right. But those will be the edges in the residual graph. Like we are making a DAG of the residual graph.
Oh, so you're doing topological sorting considering the residual graph,
Right.
but putting the edges in the original direction.
Right. Any other questions? Red edge in the residual graph, right? So in the residual graph, all edges have same direction, but because blue edges were carrying flow, their direction is reversed in the original graph.
Any edge is reduced graph, it carries flow, it's a cut edge.
Like in the reduced, like in this condensed graph, any edge that carries flow is a cut edge. Any other questions? Okay, so this gives a oracle of order n space and order one query time. And one thing that we are using here is that whenever we are given a failing edge, that must be an actual edge in the graph. If it's not an actual edge in the graph, like if you are feeding also arbitrary pairs of vertices, then the space will blow up to n square or n into lambda. Okay. Okay, so now we'll move to the question of extending this data structure to dual failures. And one thing that we'll crucially use for dual failures is the fact that if a failing edge is inside an SCC, then it cannot reduce the min cut. So all the min cut edges are going across the SCCs, but if an edge was inside the SCC, then it cannot be the min cut edge. So this we'll use for dual failures also.
Before that, why is the space order n and not order m?
So what we need to store is just the SCCs and the topological ordering.
And the cut edges.
Uh,
Sorry, the cut edges.
so we don't need cut edge because the black edges will already be inside an SCC. The red edge, like we look at x and y and we look at topological number of x and y, and depending upon which one is smaller, we'll know whether it's left to right or right to left.
Sorry, I remember you had lambda times n in this case, but that's
So like we'll need lambda into n if the input is also consisting of arbitrary vertex pairs, just to know whether it was original edge in the graph or not. Um, So I'll skip the max flow oracle. So we now come to dual failures. So for dual failures, we'll use two results as a black box. One is result which we call fault tolerant flow family, and another is an existing result on fault tolerant SCC oracle. So as we already saw that the SCC structure is useful in telling the values of min cut after failure. So for dual failures, we use an oracle to report SCCs or strong connectivity information under failures. So first result that we obtain is fault tolerant flow family. So to understand this, let us consider this example of a graph which is having two S to T paths, and suppose the the ST cut is of size 1, and these are the two cut edges. So basically we can get, if the graph is having only two cut edges, then we can get two paths such that these two paths are overlapping only on the cut edges. So one path is the red path, another path is the blue path. So suppose the graph is just having these two paths. Now if I fail an edge on the blue path, can I say that the red path is a reachability certificate? Like using the red path, we can we can go from S to T. So basically, like if an edge fails on the blue path, then red path is a reachability certificate. If an edge fails on the red path, then blue path is the reachability certificate. But if an edge, if the failing edge is a cut edge, then the reachability is broken. Now we generalize this thing to flows. So basically, the red path is a S to T flow of value 1. The blue path is a S to T flow of value 1. So we have two flows, and as long as the failing edge is not a cut edge, either of these flows remain intact. So this is when the min cut size is 1. We try to extend this to the scenario where min cut size is more than 1. So basically what we show is that we can get a collection of flows. So we can get a family of flows f0, f1, f lambda to f2 lambda. Like this is a family of 2 lambda plus 1 flows. Such that if you give any filling edge E, then there is some I satisfying that Fi is a ST max flow in G minus E. So though the number of filling edges can be n square in the worst case, we show that we just need to store 2 lambda plus 1 flows if there is a single failure, and one of these flows will be a valid flow. Is this statement clear to everyone?
Is this only unweighted?
Yeah, it's unweighted only. And this works only for single failure. Like if there are dual failures, then the size becomes at least omega n. So when a edge is filling in the graph, then we can have two scenarios. Either the flow remains same or flow value decreases by 1. So basically we can partition this into two sets. Like the first lambda plus 1 flows are actually the max flows in the graph, and rest are max flows in the graph when flow reduces by value 1. So to get an intuition of how do we get this 2 lambda plus 1 flows, let us first consider the scenario where so let us consider the scenario where the filling edge is not part of the cut, and suppose we have just considered the scenario of lambda equals to 1. So suppose we want to find this red and blue path. Can anyone tell how we can find these red and blue paths? Send. Mm. So like one thing we can do is like suppose you already know the cut edges, then you can increase the capacity of cut edges by 1. So suppose I make this capacity as 2 and this capacity as 2. Then the max flow will become 2 and you can compute a max flow of value 2 and that max flow will correspond to this red and blue path. So similarly what we do is in an arbitrary graph like here we can make the capacity 2, so we take an arbitrary graph and for all the cut edges we set the capacity as lambda plus 1. So here the cut size is 2, so capacity that we set is lambda plus 1, which is 3. For remaining edges we set the capacity as 2 and we compute a max flow in this graph, and as the max flow of value 2 can be decomposed into red and blue paths, so we show that the max flow in this new graph can be decomposed into a collection of lambda plus 1 flows. So this is just a high level idea of how do we get fault tolerant flow family, and if the flow is if the failing edge is decreasing the capacity of the ST min cut, then we can get then we'll have to extend this, and this extension is much easier than this decomposition that we get. So like this is this is just a rough sketch of how do we get fault tolerant flow family, but what we'll see is that this fault tolerant flow family can give a very easy to design oracle for reporting min cut under dual failures. So the first tool that we'll just use is that we have a small family of flows. So I'll skip this. The second tool that we use is what is already known from 2017, that we can get oracle that can report strong connectivity information after failure. So if there are no failures, then it's easy to identify two vertices that are strongly connected because we can just store the equivalence relation. And if there is a failing edge, then to report the strong connectivity, we can design an oracle of order n size, which given any failing edge and any pair of vertices, it can tell in constant time whether two vertices are strongly connected or not. So basically, like in the original graph, we can have a SCC like this, but this SCC may break. So
Some people cannot see this.
okay, so in the original graph, we can have so suppose this is an SCC. This SCC can break after a failing edge is given to us, and suppose we want to still query whether X and Y are strongly connected under this failure, under this failing edge. So we can design a data structure that given any X, Y, and E, it can answer in constant time whether X and Y are strongly connected or not. So this is the second result that we'll use as black box. So now we'll see the oracle for dual failures. So our input is two failing edges, and we'll just we have to just report the size of the ST min cut on these failures. So this oracle is just a 4-step algorithm. So suppose this is the graph and E1 and E2 are two filling edges. So first we'll just fill one of the edges, say E1, and if there is one filling edge, then we can compute the flow after that failure. So the first black box result that we are using is a fault tolerant flow family. So suppose the edge E1 is filling, then we can know what is a max flow in G minus E1. So we can have a family of just order lambda flows, and mm, from this family we can efficiently compute the max flow in G minus E1. Now what we have to do is we have to just check whether on failure of E2 F is affected or not. Um, so like in this diagram, this is a flow F, which is a valid flow for the graph G minus E1. Now we'll check if F of E2 is 0, then failure of E2 doesn't affect the min cut size um, because F of E2 is 0, so we can just return the value of F. Um, if F of E2 is 1, then either it will be participating in a min cut in G minus E1, or it will not be participating in a min cut. So does can anyone tell like how we can distinguish whether E2 is like suppose F of E2 is 1, then how can we distinguish whether it is a min cut edge or not?
Like what we did in one failure case.
Right. So like we have to just check whether E2 is a inter SCC edge, or it is an edge lying within the SCC. Now we'll have to check this in the residual graph of G minus E1. So like we have this family of flows. For each flow we'll compute the residual graph. The residual, like the family is order lambda size, and the SCCs of the residual graph will just take order n space. So we'll just check whether the endpoints of E2 are in same SCC in G minus E1 sub F or not. So if they are in the same SCC, then it's not part of the min cut, and we just return the value of F. And if it is in different SCC, then the flow will decrease by 1.
Depending on the direction. Do we not need the direction?
But we have already assumed that F of E2 is 1. Like because F of E2 is 1, it must be a min cut edge if it is inter SCC.
Also, sorry. The first step, do you want to do this in constant time, the very first step? How would you determine which one of these two lambda plus 1 flows is the one we are
So we just store a mapping from edges to the flows.
then
So like we just need to store for those edges that are participating in min plus 1 cuts. So min cut edges are lambda n, and edges that are participating in min plus 1 cut are also order lambda n. So we show that only lambda n edges are essential, and then we map edges to the flows in A. Now so one question is like we have flows and we are storing residual graphs for those flows. So we are storing G of F but not G minus E1 of F. Can anyone guess how do we compute G minus E? Like we know like so basically for each F belonging to A, we can store G of F, but question is we can like how do we get G minus E1 of F? Yeah, using the SCC oracle. So basically like G minus E1 of F will be just GF minus E1, and we can use the SCC oracle to check whether endpoints are in the same SCC, and if they are in the same SCC, we are returning value of F. We can detect this in constant time. Otherwise, we are returning value of F minus 1. Yes.
The flow of E1 is 1
Flow of like f is max flow and g minus e1. So f of e1 is 0. And we are just distinguishing between f of e2 is 0 or 1. Any other questions? So this is how we report the size of the min cut. We also show that we can slightly modify this algorithm to report the exact min cut as well as report the updated flow. So like for k failures, we use something totally different, and um, like first we studied a sub problem where we have to tell whether the min cut size reduces by exactly k on k failures. This we show is easy, and then we use something called flow augmentation in digraphs, and what this says is that suppose you have a minimal cut, then like you can add some extra edges, like you can have these extra edges, and after adding these extra edges the minimal cuts become minimum cuts. And for each cut there will be a different collection of extra edges that we can add, but these extra edges turns out to be very few in count. So the extra edges, if you are looking at minimal cuts of size up to k, then number of extra edges will be just some fk into log n. So this was shown in a recent stock paper, and using this we get our oracle for k failures. So I'll skip these. The final result that we get is that there is an order n size oracle for k fault tolerant ST min cut, which has order log n query time. And we also show that if lambda and k are not constant, then we can improve the oracle space to just lambda to power k into n. So I'll skip lower bound also. So I'll end with some open problems. So first open problem that I'm interested in looking at is our current oracles have space which is lambda to power k into n. But if we don't care about the query time, then it's known that we can improve the space to lambda into 2 to power k n. So whether we can improve the space of our oracle while still having a constant query time, and if not for general graphs, then can we improve it for DEX? Second problem that I feel is interesting to study is the oracles that we saw just now were for a fixed source and a fixed sink. So can we get an oracle where the sink is arbitrary, so it's a part of the query? So currently there is no oracle which has sublinear query time and subquadratic space. And a much simpler version of this will be just answering the reachability. So for reachability also, currently we don't have a subquadratic size oracle for single source and all destination setting. But I feel like using some hitting set ideas we can get subquadratic space and sublinear query time, but ideal goal will be that we obtain a linear space oracle with a constant query time. So if you have to answer reachability for arbitrary sink for k failures, if you are happy with the order n query time, then we can get order n space. But currently we don't have a constant query time. So we can get a constant query time if we allow n square space. That's a result by Thatchpole. But question is Can we get subquadratic space for S cross V setting? And so that's all. Thank you. Like even for yeah, like even if lambda is, you need order n omega n.
Welcome Dr. Deepanab Chakrabarti for his talk here. Deepanab did his PhD at Georgia Tech, after which he went to University of Waterloo and University of Pennsylvania for his postdocs. After his postdoc, he worked here in Bangalore at Microsoft Research for 5 years before joining as a faculty member at Dartmouth. So I'm hearing a fun fact from Professor Arindam that while Deepanab was co-offering a course with Arnab here at IISc while he was a researcher at Microsoft Research, that's when he found his love for teaching, and I think that might have had some impact in him moving to academia from the industry. So without further delay, let me welcome Dr. Deepanam for his talk.
Okay, so thank you. Yeah. So first of all, thanks to the organizers for organizing this and also inviting me. It's great to be back at IISc. Yeah, indeed, it's true. So around 10 years ago, I taught an approximation and randomized algorithms course while at Microsoft here. And I enjoyed this thing of talking to students. So I'm happy that I'm continuing this. Okay, so I'm going to talk about something actually work. I'm going to talk about this thing, graph connective linear cut query. So if you had Danfon's talk yesterday, he was talking about this cross paradigm things, and there were many things, and query models was one of them. So I'm going to do a sort of deeper dive on this query model, in particular this cut query model. It's going to be like I thought it would be like a survey style talk, but there's just too much to even talk in 1 hour. So I'm going to talk about some stuff of it. Please do ask questions. It's going to be very basic. I don't think I'll go very deep. You should be able to understand everything that's going on. So ask me questions, and if we run out of time, that's also completely fine. Okay, so let's begin. So in general, as I said, the class of problems that people have been looking at, it's sort of for the last maybe 20 years or so in some form or other, we're looking at this query access model. So traditional model is this: you have all the input in your RAM, you can do whatever you want to do with it and create algorithms. And since you can do whatever you can do with it, we don't really have very good tools to prove lower bounds. So we don't know our limitations, we have conditional thing. But if we have some, if you tie our hands behind our back, we can access the query only, data only via certain APIs or queries, then maybe you could hope to prove, understand both the powers and limitations of these things, of algorithms and the structure of this thing. And that has led to various kinds of queries. So I'll not go over all of them. So one is famous in sublinear algorithms, where you really want to design algorithms faster than even the size of the data. Then you allow these local queries. And again, I'm talking about graphs here, but the thing actually can be asked for any kinds of inputs, any kinds of strings and stuff. So in graphs, there are these local query models where you can get a vertex at random. You can query local information like its degree and its neighbors. And there are many problems that have been studied in this. As a whole, courses can be written on that. The thing that I'll focus on today are more like global queries on graphs. In particular, we look at cut queries, but you can think of that given a subset of vertices, is there an edge in there? Given a subset of vertices, how many triangles are in there? Suppose you could have such queries. Can you design some graphs, algorithms for using these queries? But there are other queries people have studied, like shortest path queries. Given a graph, two vertices, I get to know how far they are. And using these queries, can you like reconstruct the graph? Can you decide if the graph is a matching or not, so on and so forth. So there are many kinds of things. And on Tuesday, we actually saw Anupam give a talk on a certain different, which is to me new kind of queries of comparison oracles, like given two solutions, which is better or not, and using this to design the best kind of things. So that's so maybe the slide is to show that it's a rich field, and it's a field where you can also use your kind of queries that might come up maybe in some domains that you're talking with a non-theorist practitioner like database person, and then come back, model this in our area and then study them. So it's a quite a interesting area, and Anupam's point of cross paradigm actually matters to design algorithms. Okay, so with all that said, I'm going to focus on, as I said, cut queries. I'm going to define the problem in a minute. As I said, the query access model, one reason to study is that maybe sometimes the graph has these queries. You don't have, like, if maybe the Facebook graph is not given to you, you can only access it via certain APIs. So there are modeling reasons to look at that. And of course, there are structural reasons. As I said, it gives you more insight into the problem, and there's a possibility of proving lower bounds. My particular motivation, how I got into understanding or looking at this cut queries, was this other thing which I'll not talk much about. The problem that I'll talk about is going to be a special case of something called submodal function minimization, which is a problem. If you've not heard of it, if you know it, you know it. If you don't heard of it, it's not going to be that important for today's talk. It's a classical combinatorial optimization problem, which is query based. So you can only access a certain object by a certain query, and you want to do some optimization on it. We don't understand this. It's one of the I think a big open problem in this area of discrete optimization the last 50 years or so. To understand the exact query complexity, it's still open. So if you want a challenging open problem which you want to work on for a couple of years, that might be it. And today's problem will be like a special case where we'll see that what people have done. Okay, so let's get. So yeah, that's the agenda for today. I'm going to talk about cut query model in particular, and in that model, looking at a particular problem of connectivity. Yeah.
And the last one, there's a poly gap between the query complexity.
Yeah, there is a polynomial gap between the query. We like to have that gap closed. So I'm going to talk about a few techniques. It's not going to be comprehensive. It's not going to be, and I'll miss out. There are people in this audience who have worked on this, and I'll probably miss out on some names of citations. So for that, I apologize already. I will focus on one technique, which is something that I learned when I was looking at this. It's a technique from the 60s, but I don't know if it is that well known. So at least one thing that you should take away is this thing for coin weighing. It's a nice puzzle that we'll come to. And I'll end with throughout we'll see that lots of things are open. So there is, and maybe even doable. So that's the agenda. Okay. So I'm going to talk for the most of like 40 minutes about graphs. And then the last few minutes I'll talk about hypergraphs. And I'll try to show why it leads to more interesting challenges that we have to face. So let's focus on graphs. Okay, so here's the basic maybe question. I have an unknown undirected graph. I know the vertices, and here's the way I can access it. Given a subset of vertices, I get to know its cut size. What is the cut size? I get to know how many edges are there, how many number of edges, which have one endpoint in S and one endpoint outside S. So when I say number, it means that it's an unweighted graph. But you could also ask the same thing. Imagine that the graph has actually non-negative weights on the edges, the unknown edges. And what I get to know is the total sum of the weights on these edges that cross the cut. So that's what I get. So let's focus on just the number for now. What's the goal? The goal is I just want to know if the graph is connected. Okay? So the graph is connected for the time being. We'll up the ante in a minute. Or this is a Boolean question. I could also ask find a maximal spanning forest, like if it is not connected. So these are the two questions. So let's see what all we can do, some sort of warm up. So first of all, here is one thing we observe right away. Given any two subsets S and T, I can actually find exactly how many edges are there which go from S and T. So this is called maybe a cross query in the literature. So how do you do it? You find the cut in S, you find the cut in T, you find the cut of S union T, and you do some addition subtraction, and that's the number of edges. So you can get that. And in particular, between any pair of vertices, this will tell you if there is an edge or not in 3 queries, 3 cut queries. And so in order n square time, you can learn the whole graph and you can solve any problem you want. So order n square, quadratic is like the trivial benchmark. So you want subquadratic algorithms. This is, I think Danupon also mentioned this. Okay, so that was one thing. The second sort of warm-up thing that we should see is that from a single vertex, we can find an edge incident on it in log n queries by binary search. Okay, so just to sort of go over this once quickly, here's what I'll do. Here's a vertex which is colored in a slightly different color on the top left. So I first query, does it have an edge from that to the whole set? And maybe the answer is yes. Then I go to an arbitrary half, and then I ask the same question. If the answer is no, then I go to the half of the other half, and I go repeat so on and so on, and at some point I find it. Okay, so in log n queries, I can find an edge incident on this vertex. Okay, so what does that immediately imply? Well, maybe not immediately, but it sort of says that I can repeat this process and implement my favorite traversal algorithm, depth first search, breadth first search, and in n log n time queries, I can find a maximal spanning forest. Okay. Now, one thing to note, I'll say this, I did not really use the full power of the cut queries. Even if someone whispered to me and say, hey, the cut is 0 or non-zero, even then the same algorithm works. All I needed to know is there an edge or not. And in particular, even if the graph was, okay, so this is, so even if the graph was weighted, this will still work. If I only got 0 or non-zero is all that is needed. And the thing that I said here is that not only can I find one edge, if I picked my sets randomly, I can actually find a random edge incident on this. So on any vertex, I can find a random edge. Again, these are primitives that will be useful in soon. And the thing that I said that it works on weighted graphs as well. Okay, so on n log n queries, I can find the whole graph. I can find the maximal spanning forest, sorry, not the whole graph. Now, one thing I'll say, if I only use the fact that it is 0 or non-zero, which means that every query gives me only one bit of information, and the fact that there are like roughly n to the n spanning trees in any graph, if I get only one bit of information per query, if I only use 0 or non-zero, there is a lower bound of log of n to the n, which is omega n log n. So if you want to beat n log n, you need to use the numbers. You need to use that the value of the cut is given, because the value of the cut can be between 1 and n, and that's a log n bit, so that does not give an omega n.
Aren't we already using the numbers when we compute this cross?
So that's what I said. So I don't. So to determine if there is an edge between S and T, I don't think I can. You can just tell me if it's 0 or non-zero, or they're equal or non-equal. That's all I need. So I need only one bit of information per cross query. Okay. But maybe the point I'm trying to make is, if I want to shave off this log n, I need to use the value that the numbers are important. And that's the one technical thing I'll spend time on. So yesterday, Danupon said he doesn't care about log n factors, which is fine if the thing is, if there's a polynomial thing. But today I'll say that, okay, maybe if you care about log factors, there's a trick to remove log factors. Okay, so n log n times. So this is like your undergrad algorithms. It's a good, people who teach undergrad algorithms, it's a good exercise to make in this for binary search. Good. Okay. So some implications right away. So if I can find in n log n queries a spanning forest, a maximal spanning forest in fact, then the other thing is that I can actually then delete that, and I can delete these edges and implement the cut query on the residual graph, because I exactly know what I am deleting. So I can find one spanning forest, delete it, I can find another spanning forest on the residual graph. And there is this beautiful, let me see. So if I repeat this process k times, so I spanning forest delete find another spanning forest, delete, and then I do this k times, I get k spanning forests and take their union. So this beautiful theorem of Nagamochi-Ibaraki from the 90s, which says that union preserves pairwise capacities of connectivities up to k. What do I mean by that? Between any two vertices x and y, if the connectivity between x and y was bigger than k, then then I'm not saying anything. But if it was smaller than k, then it will be equal to that in the union of the forests. So it preserves all the capacities up to that k. So in particular, if the min cut was less than k, then the min cut, and between say x and y was the min cut was less than k, then this min cut is also less than k in the union. And the union I got in my hand in n log n times k queries. So in particular, in k n log n deterministic cut queries, I can decide if the min cut of the graph is at most k or at least k plus 1. Okay. So maybe what I'm trying to say is that this is again the cross paradigm thing. So once I got it, I can use these facts from sequential graph algorithms to get something in cut query algorithms. And more is true. Here's another fact from, so this is from 92, and here's a fact from.
The deletion does again require like values, right?
Delete.
So if you say delete it, and effectively you just run the query and look at pairs.
Yes,
So
yes, deletion required. Yeah, this now I'm back to the world where I have cut queries. You're absolutely correct. If I want to simulate, just to sort of make sure everybody gets what Siddharth's point is, to delete a set of edges and then simulate cut query in the residual, I really need the values because I'm going to subtract the number of edges in that. Absolutely. Good. So here is another fact. Here is a theorem from 2020, I believe, by Kafani, Novici, and Thoru. This is just a graph theory fact which says, I have an undirected, but now it's a simple graph, so there are no weights. And every vertex samples two random neighbors. Now, after sampling the two random neighbors, I get some connected components, I contract them. Two things happen with high probability. Actually, so if the minimum cut is k, in fact the following happens, if the minimum degree is k, which is only bigger than the minimum cut, the number of vertices in this connected component shrinks from n to roughly n by k. This is not true if I just did one neighbor. If I just do one neighbor, it may not shrink that much. But if I do two neighbors, it shrinks significantly. So my new graph has roughly n by k nodes. And the second thing is that non-singleton, if the minimum cut was a non-singleton cut.
So Deepak, I'm sorry, I guess I did not follow your contraction process. So vertex V chooses two neighbors?
Every vertex chooses two neighbors.
Okay.
And then you can take the union of these two. So I might choose you, you might choose me, in which case we didn't get anything new. But every vertex does this. So there is this 2n sized graph at most. And now you contract the connected components. These connected components, I'm saying, have n prime nodes. So n prime will be significantly smaller than n by a factor of their minimum degree. That's one. The second, if the original graph had if the minimum cut in the original graph had at least two nodes, so it is not a non-singleton cut, then it is preserved in the non-contracted. It is not contracted out. That happens with constant probability and you can do repeat. So that's pretty nice. It only holds for simple graphs. It does not hold for multi-graphs. So what does this mean? It means, so I could find random neighbors with cut queries. So I can implement this, okay, in n log n time or 2n log n time. I can do this contraction. And then in my new graph, n has become n by k. And I apply the kn log n, this thing, to get basically an n log n time Monte Carlo algorithm for minimum cut. So in a simple graph, finding the minimum cut can be done in n log n time. At least we know n log n time Monte Carlo algorithm. Yeah.
How do you simulate the contraction with this cut query?
So you just the vertex, every time you have the subset S. So whenever you wanted to query, you'll just for example, capital A is a contracted set of vertices, capital B is a contracted set of vertices, and I want between A, N, and B. I just query A union B.
Okay.
I am only doing cut queries, right? So contraction is actually a simple thing to implement using cut queries. Any questions? Yeah.
So I missed, how do you do cut query after removing the spanning trees?
So if I remove the spanning tree and I want to do the cut query on the, so a subset of vertices, so I do it in the original and I ask, and then I look at my spanning tree and see how many were crossing them and I just subtract. So the cut query is linear in the edges. If I know the edges, I already know the edges of the spanning tree, I found them, then I can just simulate it. Did that make sense? If it didn't, I'll explain again. So I have,
Same time.
huh?
It takes same time.
Time I'm actually not even bothered.
Sorry.
I only do the query of A in the original graph, and then I look at my spanning forest and see how many edges from this spanning forest is crossing A, and I just subtract. And that's exactly the cut query on the residual graph.
Would there be repetitions because you are querying probably like similar things, right, over multiple deletions of the spanning forest? So then you have results from the old queries. Like then can you get like better?
That's a good question. So the question is, it might be that I'm querying the same set multiple times in my accounting. Can I get a saving by seeing if I? So I don't know if that gives a saving at all.
How bad is this algorithm? Choose a random node and a random edge and contract.
Random node and a random edge incident on it only once.
And then contract and...
So every node does that.
No. One at a time. The Karger's
Okay.
random edge
So how long does Karger's algorithm take? Even if you do Karger-Stein, it will take n square. So you need to, the failure probability is 1 over n square of Karger, right? And n square is a trivial bound that I don't want to. Okay. Good point. Other questions? Okay. So what is the next slide is not. Okay, so we have seen in simple graphs an n log n time Monte Carlo algorithm to find the minimum cut. Okay, so why am I interested? So maybe I'll bring back submodel functions a little bit. So a cut function is a special case of something called submodel function. In fact, it's a symmetric submodel function. And any general symmetric submodel function can be now minimized in O tilde n square queries at the state of the art, if you don't care about running time. Any symmetric submodel function. And there is no superlinear lower bound node, even for deterministic algorithms. Okay? So even an n log n lower bound would be, some progress. And in fact, for asymmetric submodel functions, recently there was an n log n lower bound. That's the best thing that is known. So, okay, so that's a fact. Sort of shading the log n is the answer order n, or it's just n log n. Maybe it's important because we don't know anything about even symmetric submodel functions. So turns out the answer is n. So you can shave these logs away for min cut. And the technique, one of the techniques at least, is that of coin weighing. So I'm going to sort of shift gear and just talk about this puzzle, which you probably have heard of. So I'm not talking about coins, I'm just talking about unknown Boolean vector. So there's an unknown 0 1 Boolean vector. And your way to access the Boolean vector, you can take any subset and you can obtain how many ones are there in the subset. And your goal is to learn X. Okay? So there's a trivial n time. I just query all the singletons and I will get them. And if you look at information theoretically, there are like n bits of uncertainty here. And again, every query gives you log n bits at most. So n by log n is the information theoretic lower bound. And what is fascinating, and this is a fact, and I'll not go into that construction, is that indeed there is a 2n by log n algorithm. Okay? In fact, it's a 2n by log n non-adaptive algorithm, which means I give you the queries. So the queries are the rows of this matrix. I give you 2n by log n subsets to query upfront. You tell me the answers, and with that answers I can determine X. And if you're interested, for non-adaptive 2n by log n is actually also the lower bound. So the lower bound can be strengthened. And it's in this area an outstanding open problem to see if you can shave that 2 out if you allow adaptivity. No one knows. It's a difficult question. Okay, but anyway, for us there's a 2n by log n algorithm to solve this problem. So actually, just a show of hands, how many of you knew about this result? So it's a spark. Okay, okay. How many of you did not heard or not from me? Okay, okay. So good. So this is an important thing, and this is actually used in at some point in all the shaving off in these cut query models that have been done. So I'm going to tell you how it is done.
Are there results that look at like non-binary? I mean, okay, kind of digress.
Yeah, no. There are so people have looked at when these numbers are between 0 and 1 to d, and whatever is information theoretically optimum is actually doable. Oh, so the other fact, and this is a simpler one. So this was when I had no idea about the vector, but now suppose I tell you I have some more. So suppose I tell you that the vector has exactly 1, 1. Now this is something that you may have seen before. I think it's called non-adaptive binary search. So binary search can tell you in log n queries where that vector is, where that 1 is, but you can also just feed in this sort of the binary. All the columns are the binary representation from 1 to n. And if there is a 0 somewhere, if there is a 1 somewhere, then that column sort of lights up. So you can create a log n by n matrix which will find you where exactly this one is. Okay. So let me go slightly to make sure this is everyone is. So if there is a vector and I know there is exactly 1, 1, there are log n queries I can make, which will tell whose answer will tell me where the 1 is. And the log n queries are precisely the columns of the numbers 1 to n. So I'm going to use this in a second. Yeah.
Generalizes this compressing.
Yes. Yeah, so I'm going to the generalization. The generalization is if I told you there are d things, then you can, there exists a d log n by log d rows matrix. So you can make it, there's a non-adaptive d log n by log d. So there's a matrix with d log n by log d rows and n columns so that their answers contains enough information to reconstruct where the d ones are. But again, if you want an open problem, no one knows of an efficient algorithm to create these and also to decode these answers. That's open. But if you are adaptively, you can get actually an adaptive algorithm. That's also a nice algorithm of Prosciutti from much more recent. Okay, so these are the coin weighing literature. So let's see why it helps in graphs. So let me show you this old algorithm of Grabinsky and Kuch, old as in from the 98 or 2000. Of just learning a hidden matching.
So you're using that counterfeit algorithm as a supporting node?
I'm going to use it in a bit, yeah. So here is so I've cut queries, now I'm back to cut queries, and I'm even promised that the graph is a matching. So again, to find, if there's only one edge incident on this, I can find it in log n queries. Everyone can do that. So n log n is clear, simple algorithm to find it. So let's do it in actually 2n queries. 2n is actually the number of vertices. So here's what you do. Okay, so this is the question. Okay, so this vector, so think of this vertex, it's trying to find this edge. So if you think of it as a vector, the incidence as a vector, it has exactly 1, 1, right? So this is 0, 1, 0, 0, 0. It's trying to find where my 1 is. And so it can do this non-adaptive binary search, which means that there are log n subsets to the right, so that if this person knew whether it has an edge to one of these subsets, which all subsets it has edges to, it can find that edge. The key point is that these subsets don't depend on the vertex. Okay. So let me see if I've written this. What we need is for each SI, we need which vertices have edge to SI. Right? So I want to know for this, so now fix this subset. If I knew this vertex has an edge, this vertex does not have an edge, this vertex does not have an edge, this vertex does not have an edge, this vertex has an edge. If I knew it for all vertices and for all SIs, then I have all the information to reconstruct the match. Okay. So now focus on this subset, SI. We need to know which vertices have an edge to it. But now this is another vector where this is a 1, this is a 0, this is a 0, this is a 0, and this is a 1. So I'm trying to learn an unknown vector for this subset SI, which is between some 0, 1 to the n. And what will I do? I'll do coin weighing. So I can learn that in n by log n queries. So there are n by log n queries or 2n by log n queries, and there are log n different SIs. So I put them all together, and I'll get my result. So in 2n, roughly 2n queries, I can get this. So summary, left side I do non-adaptive binary search, right side I do this Lindstrom or whatever coin weighing of 2 and by 1. And it together gives 2. It's a very, very neat algorithm. Yeah.
What about general graphs?
So Grabinski and Kucherov basically said you can do this n square by log n now for general graph. Every node is trying to find its neighborhood. Just do coin weighing from everywhere. And they said D regular you can generalize to order ND. And then the whole thing started, and we basically know general graph reconstruction is, I'll write what it is, but basically whatever is information theoretically lower bound, that has been reached. Right? So if I have m edges, then if I promised m edges, then you can have an m log n by log n query algorithm for any m edge. Yeah?
I meant matchings in general graph. Oh, you don't know the bipartition.
We can do that also in order. Okay, so this is the fact that has been, this is like late, like the culminating thing is choice work from 2013, and I'll tell you what the culminating work is. Basically says this, there is an algorithm which makes these many queries, and it even works when the graph is weighted. So I'm getting just weights, I'm not getting just the numbers. And the star asterisk here is that it's a randomized algorithm. If you want deterministic, there is a plus log m factor that you have to pay, which has not been removed yet. Okay, very slowly, but that's fine.
To learn entire
Yeah.
graph.
This is for the entire graph. And again, if m is n square, this does not really give you anything. Okay, now let me move to a result of Shagnik and Danupon and 4 other authors. I'm going to do one part of it, the simple part of it, and I'll mention what they really get. But this is very nice, very cute algorithm. So we'll see that we can get now a spanning forest in n queries. Okay. So here is the algorithm. It's a Boruvka style algorithm, the thing that Danupon mentioned, the cross-cutting paradigm MST algorithm. So let's see, what is it? It says, let's do a random bipartition first. Okay. And what I'm trying to do, so these are like the connected components currently. Initially they are all singletons. And in each phase, every connected component is trying to learn one edge to some other connected component. And if even a constant fraction of them succeed, making only order t queries, then the number of connected components has dropped by a constant factor. I'll repeat, geometric sum, everything can be done in order t. Okay? So that's the main goal. Spend order t, or in the beginning order n, cut queries to shrink the number of connected components by some half or 1% even. Okay, so that's how it goes. So first it does a random bipartition, red and blue, and these red vertices are trying to find blue neighbors. That's the goal. Now it's not a hidden matching anymore. The graph between them is arbitrary currently, but you'll see a trick to basically bring it into a hidden match. So that's the goal. So first step is a bucketing step, which buckets by degrees. Okay. So let's just assume all degrees are the same for the time being. Okay. So we bucket by degrees. So this is a bucket which have all degrees are roughly 2 to the I. So between 2 to the I, 2 to the I plus 1. We want to find, so we can find how many blue neighbors are there. So blue neighbors between this bucket and that by just one cross query, which is again 3 cut queries. Okay, whatever we're going to do, we're going to now sample vertices on the blue side at the rate 1 by degree, 1 by 2 to the I. Yeah. Yeah.
So how do I do this bucketing? Like, I mean, the only thing I have access to is your.
But I do know the degrees. In n, okay, so maybe I should have mentioned. So the number of vertices between red and this blue, I can do it in one cross query or 3 cut queries. So I spend n time. My budget is n. N time and find their degrees. It's a key point because it's going to, in 2 slides it will be a problem. But right now I know the degrees, which is the how many neighbors are.
Even the blue degrees, right?
Blue degrees, yeah. For me, this is the only graph now. So I can find that, and now I've sampled at 1 by degree. So what will happen, roughly? So with constant fraction of these, we'll have exactly one neighbor here. Okay, and I basically want to learn that matching. So that's what's going to happen. So let me see if so every vertex has exactly one neighbor with some constant probability. I can actually find which vertices are there by again doing n queries or just these many queries. and I keep them, and I basically find the matching. So this is okay, it's not a matching, it's sort of matching on one end. This is the surviving vertices, they have exactly one blue neighbor. But there are basically the same algorithm that we saw for the hidden matching works for this, and I can find this in ordered T queries. So in ordered T queries, a constant fraction of the vertices have found neighbors, and I just repeat this, and this is the fact that they have. It's a very nice, it's a Las Vegas style algorithm which makes order n queries in expectation, and it finds the spanning forest of an unweighted graph. Okay, so let me say that this does not work with weighted graphs as is, and the main reason is I don't know the degree, as in the number of blue neighbors, by making when the graphs have weights, because the weights just tells me how much weight is going across. And indeed, so one thought might be, okay, let me spend some time and try to find the number of neighbors. So there's a paper of Vitarka, Gunjan Kumar and Kuldeep Means that estimating like the support when you have weights takes superlinear queries. But nevertheless, this is a paper with so anything that I've done in this is with my student Hangla, at least for this talk, that actually even when the graph have weights, you can still simulate, you can still run, you can find a spanning forest. And the idea is, instead of sampling from the red side, you sample from the blue side. So basically what you do is you sample a vertex from the blue side aggressively first. You only sample everything with 1/n probability. And then you learn the whole graph. How? By using the graph learning algorithm. And then you remove whatever you have learned. Suppose you learned an edge between this, then I don't want anymore. I found this person is already connected. The next time I sample, I only learn the graph between, like I increase my sampling probability and I learn the graph between this and the remaining vertices that are remaining. This is sort of, if you were in Sanjeev's talk about this, you increase the rate at which you sample and then learn stuff. This is the kind of idea. What can be shown, it's not too difficult, is that this process, what is the worry? The worry is that I'm spending too much time to learn these graphs, because the graphs might get dense. And if it's dense, learning them takes that much time. But we can show that the total density of the graphs across all iterations remains linear. Okay. So that gives you basically that the weighted, even in a weighted graph, you can learn a spanning forest in order n time. Okay, so that's maybe all I wanted to say about graphs. So let me show the sort of the state of the art of graphs here. So we saw this. This is the order n time for unweighted, and then we could do it for weighted, but it's still randomized. So here is a problem which I think is a cute and open problem. Suppose I want to be deterministic. So we could, with some work, again using coin weighing, shave off a log n factor from the log n in the case of unweighted graphs. So the answer is not omega n log n for deterministic algorithms. Just I want to find if an unweighted undirected graph is connected or not. But can you actually do this in linear number, like order n queries deterministically? I think it's a cute question. And whatever we do does not work for weighted graphs. So weighted graphs, still the binary search is the best known. So that's for connectivity, whether the min cut is 0 or not. For the global min cut, we saw an n log n time algorithm using this shrinking. Now if you think about it, there were two things. One was a Nagamachi-Ibaraki of finding spanning forests. That n log n became n, because that's what I showed. But the other thing of sampling nodes, that also is n log n time. So that n log n is hard to remove. So there was this beautiful extension of this Kafari Nowicki Thoru paper by the paper of Shagnik, which they call star contraction, and they can get rid of this log n. So that's a beautiful thing. You should ask Shagnik more about it. But it's I think it's a very nice generalization of that GNT paper. So the state of the art is, on a simple graph, you can get order n Monte Carlo global min cut. And Danupan already presented the main ideas for weighted graphs, which is a completely different thing using Kargar's tree packing algorithm that can be simulated in cut queries. This is n polylog n. These are both both randomized. Funnily enough, for ST min cut, so ST min cut might be simpler than global min cut. Global min cut is doing sort of all pairs min cut. But here, we don't have linear arithmetic algorithms. So for unweighted, I believe, undirected, I believe the best is actually Danupons with his students from upcoming SODA, which is n to the 8 by 5, this is a Monte Carlo. And if you want deterministic, Hachapal and Aditya is also here, they have an n to the 5 third deterministic. And then using this, they get, I think, for here.
Yeah, same n.
But why is that better than n?
No, it's deterministic.
Deterministic. Sorry. Yes. So this n to the 5 third can get this n to the 5 third using the de-randomization of the isolation cut framework. So that's also a very nice work. But as far as I know, for weighted ST, nothing better than learning the whole graph is known. So that's the status. And if you say the graph is directed, I think Danupon already mentioned this. So question mark means nothing better than the learn the whole graph and do thing is known. Maybe a log n can be shaved. Or no, I don't think so. I think learn the whole graph and do whatever you want kind of application.
So for the directed case, I think you can get n square by log n by the coil weighting figure.
Yeah. So that's what I said. Nothing better than learn the whole graph or learn the whole cut
That's
structure.
our underlying undirected.
Yeah. So that's way more than what you need.
Yeah,
So
exactly.
doing nothing better than doing way more than what is needed. Those are outstanding questions. Yeah, Shagnik, comment.
Small comment. You cannot even learn the whole graph with the directed.
Yeah, by learn the whole graph, I mean learn the whole cut structures. I can spend n square by log n, and then I can simulate every cut. So that's what I meant by learning the whole.
Run the underlying undirected graph and run a flow on it.
Yeah, you can do that and learn the whole, like after making, let me repeat what I meant. After making n square by log n queries, after that any subset I can simulate the cut query without asking the query oracle again. That's what I meant.
Are there like interesting graph classes where like the top left, like the order in question you asked is there?
If the number of edges is linear, then I can learn the whole graph.
Okay.
So I think, I don't know. So there might be, but I'm not aware of works that I've looked at.
To study some approximation question, for multi-cut or other question, for example, or even this question, let's say approximation but in linear time, or in NP-hard question you want to get near linear time, but you can.
So NP hard questions I am not aware of. People have looked at. That's a good question. Approximation is ST min cut approximation being looked at in which beats like near linear time? I'm not aware of. And everything else is sort of very close to exact. So maybe that's a good question. And I think I have a slide on approximation for hypergraphs, but as an open question. Try min cut. What is it? So yeah, so I'll say maybe no. I'm not aware of right away. Like these are NP hard questions, right? Like, oh no, you mean the 3-cut? Yeah, I don't know. I have to think about it if there's something can be done in this technology. Okay. Yeah.
So I think for approximating some modular function, they have one result known, which is a little better than n squared, or not really better than n squared. But I actually forgot the exact exponent.
So it's a different notion of approximation. For submodular function, it's additive in the submodular function minimization. And I think the question was for multiplicative. I think multiplicative, nothing is known. Yeah.
Does using coin weighing also help to learn the construction of max instead of min cut?
What is known for max cut? I don't know what is known for max cut. I don't know if the following is known, that you need n square to learn max cut. Exactly.
Okay.
There is a paper on max cut though from last year, ICAL, by Weinberg and others, but I don't remember. As I said, there are lots of works, and you can ask various questions, and we were all interested. So let me, in my last 15 minutes, sort of pivot to hypergraphs. So this is what my students' main thesis was, and let's begin with a challenge with hypergraphs. So one challenge out front. So what did we do for graphs? There was a benchmark of n square because I can learn the whole graph. That is out of the window. That is out of the window because of the simple example. There are different hypergraphs. As this is one example, you don't have to stare too hard at it. So there are different hypergraphs which have the same cut profile. So you cannot learn the hypergraph. In fact, you cannot even learn one edge, as in naively. And so all these, algorithms for hypergraphs, which so let me come to that point in a minute. So you cannot learn the any single hyperedge, at least naively I can do work. So that's one problem. But nevertheless, you can solve the minimum cut in I think whatever submodular function time is the best known time that I get, which is roughly n square. But there was a very simple n cube time algorithm from the 90s, which maybe I'll not go into, but let me stick to connectivity. Let me just make this observation that connectivity is still sort of simple. Like you can still learn the connected components in n log n time. And the reason is, so if this is my hypergraph, I can look at the clique completion graph, right? I replace every hypergraph with a clique. Of course, that's in my head. Now I cannot simulate cut queries there, but I do get cut 0 or non-zero there. And you can use just that information to determine the connected components in that graph, which are the same as the connected components. Okay. But using just that information, you cannot shave off that log n. So n log n is still the best. So what my student I did is that we can solve the connected components in hypergraphs also in order n, randomized, expected. So same thing for the graphs. And as one tool, we needed to use the weighted graph cut query spanning forest algorithm. That was one tool. Then other tool is what I'll spend maybe the next 5 minutes about. It's another cute problem. So before I
How do you simulate cut equal to 0? Earlier you need subtraction, right?
Yeah, so you can still do that even if you don't do that subtraction. What you need, so let's take this offline. You can still do it. You're right, the subtraction thing is not, but you can still simulate using the hypergraph cut query. You can still simulate the correct information you need there. You might be wrong, like the cut. You can just say, here is my cut. I'll use the same cut query. You might be wrong, but the binary search will still take you in the correct direction. So maybe this is not the right. You can simulate that n log n algorithm in this graph. That should be the right thing to say. Okay, so let's look at this question, which is a standalone puzzle, which I also, it's a cute puzzle. There is a hidden partition. Okay, so why am I looking at partition? Because partitions are very special hypergraphs. In fact, they are hyper matchings. So just like we started out in graphs with learning a hidden matching. Now here is a hyper matching, which is just a collection of hyper edges. But forget about hyper edges. You think of it as a hidden partition, P1 to Pk, and I want to recover this. These are the connected components of this hypergraph. What do I have? I have access to cut queries. Turns out it's going to be slightly simpler to look at slightly different queries called rank queries, which is given a subset of these universe. Tell me how many parts it hits. Okay. So in fact, for this example, both the cut query and the rank query is 2. But if this set contained one part completely, the cut query will say 1, but the rank query will still say 2. Okay. It's not really difficult to make n cut queries and find one representative from every part, and after that rank, and keep them aside. Rank queries and cut queries become the same. So just think of them as rank queries. And why am I calling it rank? Because if you've heard of matroids, a partition induces a partition matroid, and this is exactly the rank of that partition matroid. So in the matroid literature, you can say, can you make how many rank queries do you need to learn this partition? Okay. So again, you can do it in, if there are k pieces, you can do it in n log k by binary search. That's again another exercise good to give to your undergrad algorithms class. And we want to know, can you learn this actually in order n? So we'll see a deterministic order n, and again we will see where these coin weighing comes. Okay, so let's see. Okay, this is a different way of looking at it. I can think of every part as colors. Maybe that's the remaining slide. We'll use this. So every part has a distinct color, and what I'm getting is any set, how many colors does it hit? That's a different way of asking. Okay, so how does this algorithm work? The algorithm works actually in a very simple merging framework. I always maintain a collection of independent sets. I'm using this meta terminology. What is an independent set? It's a set where every element in that set is of a different color, comes from a different part. So I'm going to maintain this collection of independent sets I1 to IT. Initially, every singleton is in its own independent set. Okay. Now I'm going to repeatedly pick independent sets and merge them. When I merge independent sets, let's see if I have. So I keep merging independent sets till there's only one left. When there's only one left, I'll get one blue, one red, one green, and one black. But I'll also remember, so the merge operation remembers colors of dependent elements, which means if I merge these two, I'll only remember this as my independent set, but I'll remember, hey, this guy got removed because of this dependency. So in the end, I will remember basically everyone's color in some sense. Okay, so how does this work? So this is the main operation. I have two independent sets. I'm always going to pick independent sets of similar sizes. So I'm going to bucket in powers. So I have these two independent sets, and I want to merge them. And when I merge them, I should get basically four colors, because the blue and blue, one blue should go away, green and green, one green should go away. But they'll also remember these things. So that's the merge operation. So that's what I want to do. And in how much time do I want to do it? So let's see what we can do. So let's see. So this is the whole algorithm again sets. I initialize these singletons. I maintain this family in powers of 2. I keep merging things in a bucket, possibly moving result to next bucket. So what I meant is I1 and I2, I3 might be twice the size, will move to the next bucket. And so in the end, there will be log n, in the end there will be only log n independent sets which will merge sequentially. Okay. So let's look at what this merging is, how to merge and how does it cost, how much does it cost. So you can see, sort of look from this picture, you can see that there is a matching that I want to learn here, right? Because this is independent, this is independent. I can think of this graph where I have an edge if they are of the same color. It's a hidden matching that I want to find. I don't know this matching a priori, and I'm going to use the hidden matching technology to find it. So first step is to recognize the common elements. So I want to know who, like this red is not repeated, so I don't want to bother with it. This green is repeated. How do I find this? Let's see. So I claim that this is actually a coin weighing problem. So I think of, so this is T is the number of nodes here. So this is a vector here where 1 says, hey, there is a partner of yours sitting in that side. 0 says there is no partner, and this 1 says there is a green partner here. So this is a hidden vector, and I want to learn it. And I claim that I have some query access on this subset. What do I mean by that? So again, I don't know the colors, I don't know anything, I just have two subsets. Given any subset, it will tell me how many of these colors are repeated there. So does anyone see how to do this?
Keep that set, look at the rank plus I2.
Right? So basically take that set, add it to I2, take the rank, see how much it increased by, you get how many elements are repeated. So on this unknown vector, which is trying to find if I have repetitions on that, I can do rank queries and find the simulate some queries on this vector. And when I can do some queries, I can just learn the vector using coin weighing. How much do I take? So there's a catch here. It could be that there is no repeated element, or there's only one repeated element, and the T is roughly of size n. You cannot do it in, so you have to pay like order log n to find it. So in particular for S repetitions, you pay something like this S by log S times log T. Okay. So if S is roughly T, then it's order 1 per repetition. Why am I repeating this? Because when I find a repetition, I sort of say, okay, look, this fellow has found his home, so I can put it in his bucket. But if most of my queries, like I make log n queries and I find only one, then I've paid log n to find this one home. So that's not really good. Okay, so so I find first these common elements. That's where I pay time, possibly more than order 1 per common element. But after I found the common elements, I just need to learn a matching, and that we have already seen that I can learn a matching in order S, which is 1:1. Okay. So after doing these two merge steps, what is the story? So let's see this. I maybe summarize here. I have two sets of size roughly T. T is a power of 2. S is the number of common elements which I don't know. It can be small, it can be large. I pay basically S log T by log S, and of course this S is extra. And what do I get? Well, I didn't say. I basically get I3 and some arrows of dependent structure. If S is large, which is roughly bigger than any polynomial T, then the total cost log T by log S cancels, which is again the coin weighing magic. Log T by log S cancels. I am paying order S to find S vertices home. So I am paying order 1 per vertex that I never ever see again. That amortizes to order n. Okay. So if two independent sets have a large commonality, I am already good. And if they have small commonality, then I can't charge it to them. But then do you see what will happen?
Commonality jumps up.
So the I1, I2 will jump up. I3 doubles in size. But the number of such merges, if I call this such a merge is bad, I can't have that too much. Okay, so I'll come between you and your lunch, so I'll spare you this calculation. But if you amortize over all these bunches, you will see that the total cost of such merges is n by some poly in this T. And you have to sum over all T. But T is a power of 2. So this is a geometric sum which will always give order n. Okay, so this is again some sort of things that we learn in algorithm analysis like EP5 or something which comes. I should have mentioned this. So Gravinsky and Kucherov also looked at this problem in the 90s, this partition learning problem, and they got an n log n algorithm, and then they asked for whether this is like a Soda, back when Soda had one-page papers. We only learned about of that paper after we got this. So this is a simple trick, but sometimes they miss even seasoned people. Okay, so that was for a partition. So my last two, you have a question?
This is adaptive, right?
Yeah. Everything is the hidden matching thing was non-adaptive, but everything else has been adaptive.
But here when you say S log T over log S,
Yeah.
figure out this vector.
Yeah.
Even
That is adaptive, but everything, the whole other algorithm is also adaptive. But that's a good question. Like, what can I do in small rounds of adaptivity or even non-adaptive? Good. So that's.
It's like that. But rank queries like finding bases of matrices. Is that
Can you hold on to this and ask me in 2 minutes? Yeah, and I'll answer that question. Okay, so let me sort of. So the connected components in general. So after doing this, so this partition is like a hypermatching. It's a very simple thing, and I for one thought that general hypergraphs. Well, maybe you should look at degree 2, degree 3. So this is really Hans doing. At some point, he realized that no, that's all we need. The partition is all we need, and the reason. And this is a slide that doesn't do justice. The reason is this notion of an independent set of vertices of this different. All of different colors. So there are now no colors anymore. So he basically, what we show is that initially we have these contracted components already. They are all singletons, and then the independent set is now a collection of super vertices which don't have any hyper edge touching them. Okay, and checking that is just 2 cut queries. So that's the definition, and that's the object that you should merge till you can't merge anymore. Right? You can't merge anymore when you have the connected components. So, not doing justice here at all, but basically you run the same algorithm for learning the partition on this abstract object of independent sets. But the merging operation is actually done not by learning the matching, but by learning, let me see if I have this. So between given two independent sets, you have to define an unknown weighted graph between them. It's unknown because it depends on how many vertices are shared between these two sets. But weighted graphs we could learn in order n times. Like a spanning forest in weighted graphs we learned. That's a previous paper of his. So it neatly came together, this and the partition thing, and together we have an order n query algorithm. So it's Las Vegas, and it uses randomization like multiple places. So de-randomizing this is a interesting open question. Again, the best de-randomize is this n log n. Okay, so what is so let me come back to hypergraphs. One big challenge is we cannot learn even a single hyperedge for sure, but the connected components anyway n log n was easy. We shave off that log n using coin weighing. Really, in the heart of it is coin weighing and other bells and whistles. But let's now think about the min-cut algorithm, like peeling of algorithm. What did we get? So even to get n log n for simple graphs, we basically use Nagamoto-Ibaraki and random sampling. None of these seem to be able to work for hypergraphs. So how do we get any algorithm for min-cuts for hypergraphs? That's I think a good question to think about. We'll need a fresh idea, I think, using cut queries. And indeed, it's sort of really, in this light, quite interesting that you can get the min-cut, not just by SFM, but by an n-cube time algorithm of Stohr, Wagner, and others. So this is, I think, a good question. If you can beat the n cube or n square, anything better than n cube combinatorial, which is efficient, will show something about hypergraphs. So that's one open question. I think it's something worth thinking about. And in fact, even the small connectivity. So min-cut says 0 versus non-zero. I think this is not even written up, but Hang basically said that 1 versus more than 1 can be done in n square, but a very ad hoc fashion. But 2 versus 3, we are back to basically running the whole min-cut. So can we get the small min-cut a la Nagamoto-Ibaraki without even finding hyperedges? So that's I think a good question to think about. Coming to approximation, can you get 1 plus epsilon approximation algorithms? For hypergraphs, 1 plus epsilon, you can get an n square over epsilon. This was also known earlier. Can we get subquadratic there? But the thing that maybe I started off with is there any way to prove lower bounds? For example, I don't think, as I was typing this, I was thinking, has communication complexity been used for hypergraph cuts? Or maybe it does not, it's much easier. For the min-cut setting, connectivity is obviously simple, but for min-cut, maybe it's a very simple problem to solve using communication. I don't know. So that's something actually, as I was typing these words, I thought of. So those are open questions for hypergraphs. So let me come back to your question. So your question was, let's shift gear and think about matroids. And if I want to just learn the matroid using rank queries. So that there's a lower bound for that. You cannot learn matroids, even for like chain matroids. But here's another open problem for the partition. So even the partition matroid, what I showed was a simple partition matroid, where the budget for every part is 1. If I have differing budgets, can you do it in linear queries? We don't know. We could do in n plus k log n, where k is the number of parts. So the number of parts was n by log n, then it's linear, but otherwise it can be as big. So that's also another question. Okay, so to summarize, maybe 3 things. One is that looking at these query model things for problems, shed some structure and makes you maybe learn new things. Which brings me to the second point, the coin weighing thing. It's a very nice puzzle. I think a very nice result, which maybe more should know about. If I had another hour, I would tell you how this coin weighing is done. It's a beautiful way it doesn't do graph reconstruction. And the second, there are like hypergraphs leads to more interesting nuances, and especially the cut query model, we can't even find a hyperedge. What do we do? I think it's an interesting philosophical question to think about. So with that, I'll leave you and let's.
This work that gave 1 plus epsilon approximation on hypergraph, which paper
This is a paper of Chakuri and Shu from Soda 2018. They do it. They were not looking at cut query model, but they actually this approximation thing is actually true for a submodular function of certain structure, and hypergraph cuts fall in that structure. Yeah, again, I did not do due diligence in writing the references. I should.
There are no other questions. Let's thank the speaker again.
Engineering at IIT Delhi. Professor Kumar completed his BTech in Computer Science from IIT Kanpur, followed by a PhD from Cornell University. After a stint as a member of technical staff at Bell Labs in the USA, he joined IIT Delhi in 2003, where he has been a faculty member ever since. His research focuses on combinatorial optimization, approximation algorithms, online algorithms, and addressing foundational challenges in scheduling, clustering, and algorithmic decision making. Professor Amit Kumar today will be talking about disjoint shortest path problems in directed graphs. Let us welcome him.
Thank you. Am I audible? So thanks so much to the organizers for inviting me and for organizing this wonderful workshop. Pleasure being here. So I'll be talking about disjoint shortest path problem in directed graphs, and this is joint work with Kirti, who you saw in the morning, and Lakshay. Lakshay is a PhD student. And also many of the slides are by Kirti, so if you see nice pictures, just mind that. Okay, so let me start by just defining the problem because it's a very fundamental problem. So what is a disjoint shortest path problem? You know that disjoint path problem, but we are also adding the adjective shortest here. So we are given a weighted graph and two pairs S1T1 and S2T2, and weighted by, I'll always assume that there are no negative cycles, so edge weights could be positive or negative. And the question we're trying to ask is, are there shortest paths between S1T1 and S2T2 that are also vertex disjoint? So for example, let's say look at this graph, and in this graph if you see, between S1T1 there are two shortest paths, and S1T1, S2T2 shortest paths which are disjoint, vertex disjoint, for example here like this. So answer here would be yes. And if I change this edge weight slightly and make it 6, then the only shortest S1T1 path is through this lower branch, and in this case the S1T1, S2T2. So this is the question we are trying to address. Okay. All right. So why are we studying this? Well, it's a fundamental problem. If you remove the shortest condition, then this becomes NP hard for directed graphs. But surprisingly, if you add the shortest condition, then it can be solved in polynomial time. And it has applications in various settings like fault tolerant routing, VLSI layout, where you not only want disjoint paths, but you also want these paths to be short. So in some sense, we are asking if these paths are meant to be actually shortest paths, can you find disjoint shortest paths?
Does the hardness also hold if for approximate shortest paths, or like what is?
No, approximate, no, if you really want shortest, yeah. Okay. So let me give you a brief outline of the talk. So I'll just mention what is known about this. And I will first look at the special setting of DAGs, directed acyclic graphs, where, as you will see, simple ideas already solve this problem. Then, we'll basically try to understand what are the structural differences between these two settings of DAGs and digraphs, and why is it easier on DAGs but not on directed graphs. So we will see what are the challenges. We'll see for a special kind of directed graphs, ideas which work in DAGs also work here, and these are basically trying to do some sort of counting. So dynamic programming with counting. So these kind of ideas sort of work for DAGs and also work for a special kind of directed graphs, as you will see. And to extend these counting based ideas to general graphs, you need some sort of algebraic approach. You need to define suitable polynomials and say that, does this polynomial take value 0 or not, or equal to 0 or not. Okay, so essentially it reduces to that problem, and then I'll mention some open problems. Okay. So let me tell you what is known for this problem. So let's look at the case where, again, two S1T1, S2T2, two pairs. So that's why the prefix 2 there. So so there's a lot of work on this problem, starting with so in the setting of undirected graphs and weighted. So the first result was by Alem and Zorev, who gave n to the 8 time algorithm. It has been subsequently improved through a sequence of works, and last year there was a paper in IISc which actually gave almost linear time, actually a linear time algorithm for this problem. And again, for DAGs and undirected graph, both settings, one can get n plus n. For directed graphs, the best known algorithm prior to our work was n to the 5n. So, and you can also ask what happens if I, instead of making it 2 here, if I ask for k SITI pairs. So what is known there? So if you look at k disjoint shortest path problem. So there, again, there's a, so the first result was by Lochet in 21. Again, they looked at undirected weighted graphs. And again, remember, if weighted, then you don't have any negative cycles. And there it was n, and in the exponent we have, k to the 5 to the k, which was improved by this paper to n to the k factorial. So, and we know by some standard fine-grained hardness kind of results, assumptions, they also showed that you cannot do better than n to the omega k. But there is a huge gap here between k and k factorial, and it's an open problem to sort of bridge this gap. So I will only look at k equals 2k's, but k equals 3 onwards, there's a huge gap there. Okay. Now you can also ask a slightly more general question, which is, so okay, so what is our result? Our result is we improve this n to the 5n to, we give an mn log n time algorithm to solve this, to answer this problem. We also extend to a more general setting. We give the first result here, and here you want to ask, like, okay, so let's say S1T1, S2T2, the answer is no. So there are no disjoint paths. But what is the shortest number of intersections you need? So you want to find, again, shortest paths between S1T1, S2T2, which have minimum number of intersections. So this is, of course, a more general problem. And again, for DAGs, or for undirected graphs, we give a linear time algorithm. And for general graphs, directed graphs, we give m square n cube time solution. But these are the first polynomial time algorithms for these problems. And again, the moment you go beyond 2, everything is open. Okay. So this talk, I'll just for simplicity, give a slightly worse bound of m square here instead of mn. And we will look at directed graphs and just assume for simplicity all edge weights are positive. Okay? Questions? Okay. So let's see what's the difference between DAGs and directed graphs and why DAGs are easier. So now look at a DAG, right? So let's say it's a directed acyclic graph. So there are no cycles. So when let's say this is S1 T1 shortest path and there is S2 T2 shortest path, and if you look at, there are some intersection points, right? So these two shortest paths intersect at a few points. The order of these intersection points will be the same in both these shortest paths. So for example, if this is the first intersection point in the S1 T1 path, this will also be the first intersection point on the S2 T2 path. Okay. So between any two common vertices, paths are aligned in the same direction. But so for example, if you look at V and W as 2 points of intersection, V appears before W in both of these paths. So it cannot happen that V appears before W in one, but not in the other. However, this property may not hold for general graphs. So you could have something like this. And now if you look at this picture, both are shortest paths. But if you look at S1 T1, so in this one, V appears before W in the S1 T1 path. But if you look at S2 T2 path, it is reversed.
Just to make sure I understand, this is just for, you're just using any two paths is the same, not shortest.
Even for shortest path, this can happen.
Even for any two paths.
Even for shortest path, this can happen. Because I can always, I mean, imagine that these are directed graphs, right? So I can always, if you switch the role of S1 T1, I mean, yeah, you can construct shortest path where this will happen. So imagine that, you know, these edges are directed like this, and there you want to go like this, right? And these are vertices.
No, sorry, I was saying the first structure holds for any path.
This is for DAGs.
Yeah, any path, not shortest.
Any path, right? Okay. So let me begin by, you know, asking, you know, how would you solve this problem in DAGs, right? And this you will see just follows by dynamic programming plus some counting kind of arguments. Okay. So for DAGs, what do we know? You can do topological sort, right? All edges can, vertices can be arranged so that all edges go in one direction. Okay. So let's ask a simpler question. Again, this is, I'm sure many of you would have solved this problem. Let's say I give you two vertices S and T, and now we are only in the setting of a DAG. And you want to count how many shortest paths are there between S and T. Okay. And this I claim you can easily solve using dynamic programming. So let's just see. So let's say that you want to count how many paths are there from S to T. And let's say you have computed this for all vertices which appear before T in the topological sort. So you look at the in degree of incoming edges into T, and you look at those vertices B1 up to Bk, all in neighbors of T, which lie on some shortest ST path. So there can be multiple ST paths, but look at those in neighbors of T which lie on some shortest ST path. And this you can discover because you can, you know, as you're going along, you are figuring out what is the shortest distance from S to each of these vertices. So you can figure out when you come to T, which of these vertices will lie on shortest ST path. So you look at those vertices B1 up to Bk, and if you are maintaining this count for each of these vertices B1 up to Bk, then you just have to add up these values. So I can compute in linear time this quantity Cs, T. Right? Questions? Right. So for any fixed source S, I can compute in linear time all the values where this is denoting how many shortest paths are there from S to a vertex X. Okay. Now let's see. Now what happens in for two pairs now? Okay. So let me give one piece of notation. So I'm going to again, instead of asking yes no, so remember we are trying to answer are there shortest paths S1, S2, S1 T1 and S2 T2 which are disjoint. Let me count how many such paths are there. Okay, so this is counting, this is saying the number of pairwise disjoint shortest paths between these two pairs. Okay, this is counting. And I want to write an expression for this. Okay, so of course it is upper bounded by this. So look at how many shortest paths from S1 T1 and S2 T2 are there, and take all such pairs. And I will subtract out the number of paths which actually intersect. Right. So I will multiply these two things, and I will subtract out the number of intersecting shortest path. And the way I'm going to subtract out is I'm going to guess the first point at which they intersect. So I'm going to subtract out here. So let's say V is the first point where these S1, T1, S2, T2 paths, shortest paths intersect. And so I'm going to count how many shortest paths are there where V is the first intersection point. And note that because it's a DAG, I can define first intersection point. Because otherwise even this definition did not make sense if it was a directed graph. Okay. So if I could sort of somehow compute this quantity, then I can compute this number, and if this number is positive, then I know that answer is yes. If this number is 0, then the answer is 2. Okay, all right. So how would you compute this quantity? Okay, so this is the expression, and note that which vertices should I sum these over? These are the vertices which can potentially lie on both of them, right? So this I can check. Okay, so this is the picture, right? So you have you are guessing the first point at which these two paths intersect. So if you take a look at this condition here, that V is the first intersection point, what does that mean? It means that, well, these two paths are shortest path. This is S1V shortest path. This is S2V shortest path, and they are disjoint. Right. So essentially, the number of such pieces here is exactly this quantity. Right. So this is counting how many shortest paths are there from S1 to V, S2 to V, at which do not intersect. So essentially, I have reduced sort of this problem. I am reducing it to solving this problem. But V is in some sense an earlier vertex. And then what happens after V? Well, all I care about is, now I don't care about how they intersect. So I will just multiply the number of such options here is just number of shortest path from V to T1 multiplied by the number of shortest paths from V to T2. Right? So this is exactly the number of pairs. So this is exactly the expression that I have here. So number of pairs of paths where V is the first intersection point. And how do I compute this? Well, this is again by recursion. I can just plug it in here in the left side here. And so computing this will reduce it to computing the same quantity for some, instead of V, you will have some W which is further earlier in the topological order. So, right? Okay, so what does, so this is the entire algorithm, right? So let's just write down what is the running time of this algorithm.
When you use the property of this, the first the previous property only at the recursion, till that point the formula is more general.
Sorry.
So you use the fact that you can recurse in a proper well-defined manner.
Absolutely. So I need to use the fact that at the time, I can compute these quantities in some order, right? So this guy will again say that what is this quantity? I'll again write the same expression there, and then again there will be some recursive thing there, but those W's would be appearing before this, right? So there's a topological order. Also, note that earlier I could not even define what is the first intersection point, right? I mean, because the orderings are different on the two paths, and this will be an issue as we go along. Right? But here it's clear. Okay. So, right. So this can be computed using dynamic programming. So let's look at the overall time complexity. So first of all, these things I'll just compute upfront all pairs number of shortest path. So remember, for one source it took me m time. So all pairs it will take mn time. So this already I incur here. Now how many subproblems are there? Well, remember S1, S2 remain fixed, V just varies. So the number of subproblems will be n. And how much time do I take at each of these subproblems? Well, if you already have these numbers with you, computing this time will take at most m units of time. Right? So then at most n units of time, because you have to just cycle over all B. So this is n square here. So n subproblems, and for each of the subproblem, it will take n units of time to solve it. So mn is because all pairs, and n square is just the dynamic programming. Sorry.
So why do you need all pairs? Sorry.
Why is it mn? Why do I need? Because I need these S1, T1, S2, T2, and then here when I do this S1V, S2V, So then I would need,
S1B and S2B.
yeah, I think
You
maybe,
get UV as well.
yeah, I think, will I need, yeah, so all the sub problems would be S1V, S2V, minus, maybe I can,
So we need to check the summation, the SIB plus BTI, and
Oh,
there it
okay,
will be
okay.
yeah, sorry, yeah,
That's
sorry.
the- that's
So
the-
VT1, VT2, yeah. Because I also need, right, good. So I need these expressions also.
Also in the
Okay.
subproblem, would you need from U to V when you go to the further subproblem? So when you iterate over W, for example, then you would need from W to V as well.
So you're saying what? If I need W?
When you go from so C disjoint S1V, S2V, you iterate over W, the previous vertex, then you need W to V?
Yeah, I need W to V also, right?
C
Yeah.
of W comma V,
Yeah.
right?
So I need all pairs, I think. Yeah. Okay. Good. So essentially, so what we have shown is that on DAX you can solve this in mn time. Now Akmal, Williams, and Wine, if you read their paper, they give a faster algorithm. This was in iCalc last year, and they would use algebraic techniques, which I'll talk about. So you can.
So just to make sure, so you actually also solve the disjoint path problem. You never really needed shortest. So is the disjoint path problem is easy on a DAG?
Oh, on that, so you're asking, do I need the shortest path condition here? So maybe.
That the summation condition goes away.
Yeah, it goes away. So it go on all V.
So you could count how many. Yes, so these guys I can count how many paths are there. No, let's take this offline. Yes, yeah. Okay. All right. So what happens in directed graphs? Why does this approach not work? And I already alluded earlier that you can talk about the first common vertex on both the paths, but here you can't talk about that, because if you look at path P1, the first vertex is V, but if you look at path P2, the first vertex is somewhere else. But you can always say, okay, let's guess the first intersection point on path P1, right? Why not do that, right? So, okay, so let's say that when you talk about the first intersection point, you also have to specify which path you're talking about. So let's say, I upfront say that on path P1, let us guess the first intersection point. Okay. So earlier, remember, so when you were guessing the first intersection point, the condition was that, what does it mean that V is the first intersection point? The only condition that you had to satisfy was that the portion of the path from S1 to V and the portion of the path from S to V were disjoint. And beyond V, we did not care. Right? Beyond V, these paths can intersect in any manner. Now, what does it mean to say that V is the first intersection point on path P1? What condition does that mean? So, because it's the first intersection point, this piece, the green piece, should not intersect P2 at all. But that means that because we are in a general setting here, this green piece has to be disjoint from this pink piece, but that's not enough. It also has to be disjoint from V to T2. Right? So all these three, the green piece has to be disjoint from both of these two pieces. So this is the condition now, right? So we say that V is the first intersection point on P1 if the portion of this path from S1 to V is disjoint from S2 to V and also from V to T2. Only under that condition V will be the first intersection point. Is that clear? Because now, if this piece intersect either here or here, it will not be the first, V will not be the first intersection point. So this better be disjoint with the entire path. Okay. So now the problem is that now my condition has become more complex. Earlier I was just saying that I was reducing to a problem of the same type, but now it's not a problem of the same type. So earlier it was just S1 T1, S2 T2 was getting replaced by S1B and S2B, but now it's no longer that kind of problem. So now I'm stuck here. Okay. So what do I do here? So let me look at a more special kind of directed graph. I'll make an artificial condition, and this is very artificial, but it will ensure that the idea that I had for DAX will also work here. Okay, so this is the definition. So I'm saying that a graph G is said to be forward crossing free. If you look at any, again, S1, T1 and S2, T2 and look at the shortest path P1, P2, suppose these two paths intersect at points A and B, okay, and A appears before B on both of these, on both P1 and P2, then the portion of the path from A to B is common in both. So let me show it by a picture if this is not clear. So let's say if you look at A and B here, so A appears before B on both the paths. Okay, but if you look at the piece of the path from A to B, they are distinct. So this will not be forward crossing free. Whereas something like this would be forward crossing free. And you will see why I need such a condition. It looks like an artificial condition, but you will see why it is very useful. So for example here, if they intersect at A, they will go along together till B. And again, when they are intersecting at X, and if they are going along the same direction, they will keep together till they separate. Now look at BX. BX is not like that because BX is, the order is reversed in the two paths. So essentially the way that these paths are looking is that the moment they intersect, and if they are going to intersect again in the future, both of them, then they just keep along together, and so on and so forth.
So the blue part and the
Yeah,
red
this is
part,
because if you look at this piece here and this piece here, they are not same.
but the cost must be the same.
Cost would be same, right? Because these are shortest paths. Right? Cost has to be same. But I want them to be really like identical. You're right. Yeah. So the cost will be same. Whereas here also this was okay, but because of this issue, this is not forward crossing free, whereas that is. Okay. So again, you will see why I need this condition. If it confuses you, just stay with me. I'll just point out where exactly we need this condition. Okay. So this is. And I'll come back to that condition and we'll see why it is. Okay, so let's again see. And why are we doing all this? Because remember, we have this strange condition here, right? I have this strange condition here. I don't know how to handle this. So I'm going to replace this condition by something which looks like this. Okay? And that criteria will be useful. Quick question? Okay. So again, this I can write as before, right? So now, instead of V being the first intersection point of both the paths, V is the first intersection point on P1, but otherwise this expression makes sense as before. And I'm trying to figure out what this is. Okay. And remember, what we said was that, what does it mean that V is the first intersection point on P1? Well, this piece has to be disjoint from the entire path. That's what it means. Now, if the graph is forward crossing free, I claim that that condition can be replaced by this alternate condition. Okay. What is this alternate condition? The alternate condition says that, well, the S1 to V has to be disjoint from this. And remember earlier I was saying that it has to be disjoint from this entire piece here. I claim it's enough to just say that the incoming edges are distinct. Why? Because, well, incoming edges have to be distinct, because it has to be disjoint from this entire piece. But suppose the incoming edges were distinct and this piece was meeting somewhere earlier, then the entire piece has to stay along. Okay, so this is where exactly I need that condition. So I can replace that condition that S2 to B has to be disjoint from S1 to B by just this simpler condition. Just that at B, the incoming edges in the two paths have to be distinct. So now I'm in a good state because now I'm reducing it to only one sub-problem of this type. And this condition now is much simpler. This is again something that I can guess. I'll show you it. So this is the reason why forward crossing free was useful. Essentially it said that if this guy meets somewhere earlier, then the whole thing has to be together. And if the whole thing is together, then these two edges will not be distinct. So just this condition is enough. And when you will see that when we go to general graphs, again I would like to get that thing. Okay. Okay. And we'll see how to get that thing. Okay. So let me quickly now write down how you will do this, how you will count this. So right. So let's just count how many. Again, let's do the same counting. So let's say this is counting number of disjoint paths from S1 to B and B to T2. So this has to be disjoint from this. This is counting how many paths are there where this piece and this piece are disjoint. Okay, and I'm multiplying this by number of shortest paths from here to here and from here to here. Okay, but I have to subtract out the settings where. So here I have not cared whether these two edges are distinct or not. So don't worry about all these expressions. So essentially I have not cared about where these two are distinct or not. So I will subtract out all those guesses there. Essentially I'm just going to guess where these two pieces could have met if B was not the first, if these two edges were same. So what would, so here I'm not caring whether these two edges are same or not. So I have to subtract out the cases where these two incoming edges are the same. So you can guess this edge which is common and subtract out all of those things. So you can just believe that. So if you really want to see the expression, basically I'm subtracting out all the settings where both of these paths include the edge AB. And so that's exactly that expression for that. So, but the punchline was that I was able to replace the second condition by the simpler condition that the incoming edges at B are different, and then you can do dynamic programming with that. You can do some guesswork and you can do that. Okay. Yeah. Okay, so you have to guess over all incoming edges at B if this is the common edge, and then you have to subtract it. Okay, so if you do the time complexity, if you figure this out, then you can find again all pair shortest path instead of mn. You can find all pair shortest path in mn log n time, and then again it's number of sub problems and the time to solve each of these sub problems, and mn log n stays as it is. The number of sub problems will now be again, if you look at it, it is S1 v comma T2. So essentially you are also guessing which edge this is. So the number of sub problems will be number of edges at most, and so you get an m square here. Okay. So the key idea here is that because these are crossing free, I can actually replace this condition of disjointness here by the fact that these two edges are just distinct, and that allows me to do the counting. So that's enough. Okay. So for if these were crossing free, I can do this. Okay. So let me now go to the setting of general graphs.
But in some, you are always solving you are actually doing the counting problem. You're not just saying yes.
I'm actually counting how many such paths are there. But now when we go to general graphs, I will not be counting. Okay. So as you can see, these ideas will only take us so far, right? What happens for general graphs? So now let me try to. This will look a bit strange, but I will define some polynomials. Okay, so and the way I am going to define the polynomials are as follows. And you will see the key idea. The key idea will be again trying to avoid those two conditions. Okay, so for each edge E, I will have a variable ZE. Okay, and for each path P, I will define a monomial. So one monomial which will be essentially look at all the edges in this path and multiply those variables. Okay, and now earlier we were counting how many shortest paths were there from S to T. Instead of counting this, I will replace it by a polynomial. Okay, so for each pair of vertices. What is this polynomial? It is just saying that look at the set of all ST shortest paths and the sum over all of these FPs. Okay, so you add up all of these. I'll show you an example. So add up these monomials over all pair shortest paths. Okay, and similarly, earlier we were counting how many shortest paths are disjoint shortest paths are between S1 T1 and S2 T2. And here I will replace that by another polynomial. Okay, and this polynomials will be again exactly of the same flavor. It will say that for every pair of shortest paths P1, P2 in this set here, right, which are of interest to us, which are disjoint, you multiply the corresponding monomials, corresponding polynomials for the path. So let me show you an example so this will become clearer. So let's say that all edge weights are 1. So if you want, these are shortest paths, right? If you are only interested in S1 T1, there are two shortest paths, the upper one and the lower one. So f of p would be where z e1, z e2, z e3 plus z e4, z e5, z e6. But if you're looking at S1 T1, S2 T2, the only pair is the green one and the blue one. The green one is essentially z e1, z e2, z e3, and the blue one is z e5, z e7, z e8. Now if there are multiple such things, then I'll look at all pairs and I'll have a summation here. Right, so there is only one pair like this, so I have only one term here, one monomial. But if there are many, then I'll. Okay. So every shortest path between S1 T1, that's a monomial. Every corresponding is a monomial. You multiply the two monomials and sum over all of those. And really, if there were no shortest paths here, I would not get this polynomial would be the zero polynomial. Otherwise, it will not be the zero polynomial, and you're trying to figure out whether it's a zero polynomial or not. Okay. Now, for reasons which will become clear later, I want to check if this polynomial is zero or not. First thing is I don't even know how to write this polynomial. But what I will show you is that you can evaluate this polynomial provided the characteristic is 2. And this is very crucial. We'll see where characteristic 2 is being used. Okay. So what I will do is I'll be able to evaluate this polynomial at any values of, you give me values of these ZE values, I can evaluate this. So if this is a non-zero polynomial, if I evaluate it at a random point, it's unlikely to be 0. And so that will tell me that this answer is yes. But I will only be able to evaluate this polynomial if I am in characteristic 2.
What is characteristic?
Oh, sorry, characteristic 2 means that 1 plus 1 is 0. So essentially think of anything where you can do addition, multiplication and so on, but 1 plus 1 will be 0. Okay. Alright, so let's move on. I have 10 minutes. So where is this property being used, right? So let me show you where this property gets used. Why characteristic 2 and how we are able to deal with this. So suppose, again, let's look at S1 T1 blue path and S2 T2 red path. And suppose they are intersecting at 2 points here. Okay. And remember what is the polynomial here? It will look at all the variables for the edges here, blue and the red edges, and will multiply all of them. Okay. Now, if these are shortest paths from S1 T1 and S2 T2, if I swap these two things here, those are also shortest paths. So those are also shortest paths. Right? So here I have P1, P2, here I have Q1, Q2. But if you look at FP1, FP2, what was the monomial here? It was just adding up the Z values for all of these edges. What happens here? This is also adding up the Z values here. So when you add them in characteristic 2, they cancel out. Okay. So essentially says that, okay, so this is the only observation where I need characteristic 2. Okay. So, alright, so it says that, if P1, P2 are two shortest paths from S1 T1, S2 T2, and the A appears before P on both, and suppose this portion is not same, they are different. So the only case where this, I'm assuming that they are disjoint here. If they were same, then of course this will not work, right? So if they are distinct, right, they don't overlap here, then FP1, P2 is equal to FQ1, Q2. So when I add up all of these things, these contribution will kind of, okay, so you see what it's saying. So now let's see. So earlier I had the count here, but now I want to write down these polynomials.
And if you have intersecting paths exactly intersected once, like across.
If they intersect one, of course they will not.
This one.
Right. So then, of course, right? So okay, good. So even if they suppose this was this was S2T2, then you cannot. Then they will not cancel out. So we really want this. And remember, this is good news for us because this is exactly the property that forward crossing did not have. If I was in the forward crossing setting, this would not have happened. This was the worrying thing. Right? Now you're saying that this worrying thing I can take care of. Right? So essentially this solves the problem. Right? So you can write down this again. Right? So S1T1 if so unlike the count, you have polynomials for them, and again you're guessing the first vertex, and it's exactly like before. Right? So and now you're guessing the first point of intersection, and then you're saying that whatever extra we counted here, which was not here, I'm just going to subtract out there. And essentially the dynamic programming, now we can sort of do dynamic programming just to evaluate this using the same ideas. Okay? So, and by Schwarzschild lemma, I can evaluate it at, if this is non-zero, then with high probability this will remain non-zero. Okay. So okay, so let me sort of so again, all of these. So C S comma T, I am replacing it by a polynomial, and you can evaluate all of these things. Let me sort of skip. Maybe I will just show you how to evaluate this. So again, remember what was the condition? The condition was that. So again, you're trying to ensure that S1 to V does not overlap with S2 T2. Okay, and the point is that if the incoming edges are distinct, right, and this guy intersects earlier, this would cancel out. So this is exactly the kind of thing which would cancel out before, right? So so you can again exactly do the same kind of operations that we were doing earlier. Okay? So everything works out as before. So I mean, one has to, of course, instead of counting, write down suitable polynomials here, but exactly the same ideas would work. So, and if you do the time complexity, it turns out to be empty. Okay. So this is the result we have, that for two disjoint shortest path in directed weighted graphs, you can solve this problem in order m square plus mn log n time. So this is a randomized algorithm, by the way, because you need to check if a polynomial is non-zero, and we are just going to evaluate it at a randomly chosen point. Let me, in the last 2 minutes, talk about how do you even extend this. So remember, what was the problem here? The problem here was that now the answer is not yes, no, but you want to figure out, the smallest number of intersections any S1, T1, S2, T2 paths will have. So I will not tell you the details, but let me just give you what is the main sort of roadblock here. Why do the previous ideas don't work? So for example, if you look at this example here, the shortest S1 T1 path is the green path, and the shortest S2 T2 path is the blue path, and they intersect at 2 points. So I don't have disjoint shortest path, and the minimum number of intersections will be 2 here. So I mean, why does the same idea not work here also, right? So again, what we do is you can again say that, look, let us try to check whether there are shortest paths from S1 T1 and S2 T2 which have at most k intersections. Okay? And can I write down a polynomial for that also? So for example, if you look at this picture here, S1 T1 and S2 T2, maybe the shortest paths have 2 intersections. So I could say that let us write down polynomial like this here, where you again multiply the monomials for P1, P2, where P1, P2 have the minimum number of intersections, or at most k intersections. But the problem is like this, right? So suppose these are two S1, T1, S2, T2 paths, and they only intersect at two points. So here, if I try to write down the polynomial for such paths, I will get f of P1 times f of P2. But again, if these are two shortest S1, T1, S2, T2 paths which intersect at 2 points, then so are these two. Where all I have done is, the red one I'm saying that instead of going straight, it takes the upper piece, and the green one now takes the lower piece. So these two are also shortest paths between S1, T1, and S2, T2, and they also intersect at 2 points. And now if I add their polynomials, I'll get 0 here. So, but there are two shortest paths which intersect at 2 points. So the same idea kind of does not work here. So one has to do more work here. I will sort of, I guess, how much time? Nothing more. So you need to do more, and you need to do a more careful counting, which I will not get into. So let me just close with open problems. So we gave an MN time algorithm, but one open question is that for two disjoint paths in directed graphs, can we also get a linear time algorithm? So there is no reason to believe that there cannot be a linear time algorithm. Now in directed graphs, what about 3? Right? So can we get a polynomial time algorithm for the 3 DSP problem? Remember the n to the k result I showed, or n to the k factorial, was for undirected graphs. For directed graphs, can you solve 3 DSP in polynomial time, or any constant k for that matter? And again, the best known for undirected graph for k DSP is n to the k factorial, but can you make it n to the k? Thanks.
So 3DSP and DAGs is also open.
K DSP in DAX.
N to the k. N to the k is like tied.
N to the k is known, right?
Do any of the other results in that table use these algebraic techniques?
Sorry?
Do any of the other results that you, not your result, but do any of the other results?
The n to the k one?
Yeah, do any of them use algebraic techniques?
No, they don't use algebraic techniques. So the DAG one linear time, they use algebraic techniques. Now these algebraic techniques have been used for other settings also, for max flow and others. But
Are there any other questions?
So can I just have maybe to understand, the only place you use shortest path was the flip thing.
Yeah.
Like that thing will not use. If you go back to that picture where the sorry, I need to go back, but
no, I think
A and
okay.
B intersected, and you flipped from
That allowed us to.
this one. So if S2 they were not shortest paths and paths, they may not be paths anymore. Because, so why is it that the AB does not contain some red vertices?
Oh, because I assume that these two are. So okay, no. So first of all, these will also be. I'm assuming that these are disjoint, right?
So they are distinct. They're not. Okay, so they're disjoint.
Let's take the next time they meet, right? Then they cannot meet in between.
No, that's my assumption, right? That remember, I'm assuming that. Oh, okay. So
no, the bottom
even if they're not disjoint, even if they intersect, right? If I flip them, they will still be shortest paths, right?
Right. But but the bottom vertex, in the blue one, the
Yeah.
Why is it not there from the B to T2 path in the red?
It is there, right? So I mean, this vertex, when I flip, this is the red one goes like this.
Sorry, I can. So it could be that bottom vertex is in the B.
Oh, you're saying that this piece could be here.
Yeah, this could be here.
Yeah, because these are shortest paths,
If
right?
they are not shortest
These are
paths.
shortest paths.
Is that the only place that breaks down? Because otherwise, I don't see anything where you are using shortest paths. Where did you use shortest paths?
Right. So let's see. I mean, okay, so good. So well, okay, let's see.
Anyway, so this is maybe we can take it offline.
So right. So I mean, I think we are using shortest path in the setting. Yeah, I guess that's the only place. Right? Yeah. That's kind of, yeah. I think so. Yeah, and when you go to k equals even 3, all of these patterns become more daunting.
Let's thank the speaker again.
Hello everyone. Hello everyone. Welcome to the last talk of this wonderful workshop. It is my pleasure to introduce you to Prof. Surinder Baswana. Prof. Surinder did his PhD from IIT Delhi. He is now faculty professor at IIT Kanpur. During his stay at IIT Kanpur, he won various faculty awards, including best for teaching, including best faculty awards. He won it for like 8 times. So that's like very, he's an amazing teacher. So his research interest spans across various fields of graph algorithms, like graph spanners, approximate shortest paths, dynamic graph algorithms. Recently, he is working in min cuts, in which he had some very fascinating realizations on which his today's talk is based. So let's welcome Prof. Surinder.
So am I audible at the end? Okay. So let me start this talk with 3 thanks. First, thank to the organizers for the kind and generous invitation for me to attend this workshop and present this work. Second, again to the organizers for doing this wonderful job actually. This workshop is really great. The way they have organized it, the breadth of these topics, the choice of speakers, and even this junior senior session actually they are extremely well. I would say that's a very great job. And last, thanks to all the speakers till now. I think these are really great talks, far better than conference talks, and they are pitched at the right level for the students and the experts actually. So that's also it. And now this is the last talk of last day also. So all the talks are great, but your mind is getting saturated. So and moreover, this is the also talk which is back to back, no coffee breaks. So I will try to keep you awake that way, and I think I will be able to do so. So let me start with this topic. Topic also, if you look at it, it looks very boring. What is compact structure for various min cuts? I'll go very slowly. I'll take various pauses in between. Feel free to interrupt me if you have any questions. Okay. So let's say what are cuts. Suppose G is a graph which is undirected multigraph. It's an n vertices and m edges. Okay, the vertices is shown there. Consider any subset of vertices A. Like this A here, and this is A bar. And there are various edges going from between A and A bar actually. Okay. So these edges which you see right now are the edges of the cut defined by A. So set A defines the cut. That is explained formally here. Cut A is set of all those edges x, y, such that x is in A and y is in A bar, or y is in A and x is in A bar. Okay, capacity of a cut, it is just the number of edges in the cut A. Fine. What is ST cut? What are ST cuts? So there is some source vertex here and sink vertex here. How to define it actually? If S belongs to A and T belongs to A bar, it's called a ST cut. What are Steiner cuts? Let me define it. So consider these golden vertices. That has to be set of vertices, and they have to be at least 2. Each set is called Steiner set. Okay? So when do we say cut to be Steiner cut? If it also separates the set. So let me say A set of vertices is said to define a Steiner cut if A intersection S is non-empty and A bar intersection S also is non-empty. So for example, as you could see here, this is a Steiner cut because some vertex is here, some vertex is there. Is this a Steiner cut? No. This is a Steiner cut again, right? So we know about ST cuts, global cuts, Steiner cuts. So point to note is the following in this case: if S is just 2, then it becomes just ST cuts. If S is n, it becomes global cuts. So Steiner cuts are basically generalizes this entire spectrum in that case. Okay, now comes various min cuts, which we are going to talk about in this talk. Global min cuts, very simple, cuts of least capacity. ST min cuts, AST cut of least capacity, and standard min cut is standard cut of least capacity. Fine. Now there have been a lot of work in the area of algorithms for these min cuts. Really huge amount of work has been done there. And let me state to you the current best results there. Basically all of them are close to linear actually. And in fact some of them are quite old in fact. Or ramp login time for computing global min cuts, and close to M you could say for ST min cuts, and also close to M even for the standard cut of least capacity. But if you look at it, look at all the algorithms actually, they just report one min cut. Only one min cut they report. Right? So why should you care for more min cuts? Let me ask some questions that will motivate you why we should go for this. So there are so many min cuts. Are they related in any manner? Second is, can we store all these min cuts compactly? Okay. And last, can we have actually a simple answer to the various queries actually? For example, you think of any of these cuts, ST min cuts, whatever, for example. Can you report a ST min cut that separates a given pair of vertices also? Does it exist? And if it exists, you have to report that cut. Report a min cut, ST min cut, for example, that contain a given S. How to do it? You would say, let's run the algorithm, which are there actually, but that is our kill actually. I'll convince you about that. There are very elegant way to answer these queries efficiently in a very simple manner as well. Okay, so we can do it in this way, but it's overkill actually. So let me talk about, so I told earlier also that there is a lot of work on algorithms for this problem. So, but at the same time, there are many compact structures exist that answer these questions very elegantly, and they are quite old as well. So global min cut, let me say 1976 was there. ST min cut 1980s, and standard min cuts again quite a lot. So results are very few in number, but they are, I would say, really fundamental results there. They deserve to be part of curriculum that way. That I must say that. Okay, so this is, we won't use such a heavy machinery for this. This structure will answer them very easily. Okay, so now this is how I'm going to organize this talk in this case. So there are three parts. Part one is very light, compact structure for ST min cuts, and here I will just basically complement what Kirti said. It's going to be very short actually. Part two in this case, compact structures for global min cuts. And third will be compact structure for standard min cuts. Okay, these first two results which are there, I must say they are so elegant and simple, they are worthy of undergrad course level actually. What about the third one actually? I would say, in fact, someone asked me during lunch time that why I'm shifted to min cuts actually. So I would say that look, I am working on various domains like spanners, solid paths, but if you look at the richness and depth, nothing like min cuts. And this is the result that convinced me actually, and I hope you will also be very impressed by this result. This is not by me, but I still feel that look, we all of us really need to basically really appreciate this result. This will tell you how rich this area is actually, how deep it is actually.
So this Preeminent min cuts are also known as terminal cuts, like some literature?
There are different terminology there, but yeah, but here I defined you, that's why we are going to focus. Okay, so let me give you the background also. How did I come across this paper actually? So 2020 I was working with my student on sensitivity oracles for all pair min cuts. So the problem is the following, that you have to build a data structure so that I give you a pair of vertices U and V and an S. And you have to report the UV min cut after failure of S or misuse of that S actually. It's typical fault tolerant problem which you think about. Okay, working on this, and then we came across this paper, connectivity carcass of a vertex subset. This is nothing but standard subset I would say here. And this result is by Dennis Weinstein in the period 1994 actually. And what we did is we, of course, by the way, let me also convey to you this very important result which maybe many students don't know actually. So we know about algorithms for max flow, fault recursion. But what is the first polynomial algorithm for max flow? Most of the people say it is Edmund-Karp algorithm, but it is not true. The first algorithm was given by Dinitz and before Edmund-Karp itself. Okay, so it's really, I would say algorithm gem, which is there in this case. Okay, and to be very frank, I would say, look, this result which is there, of course, many people don't know, but it's again very, very great result. We found this paper, this result which is there is equally impressive and very fundamental. We used it to solve our problem. This played a very crucial role there, but we used it as a black box only. And we tried to basically go through it, the paper, try to understand it, and we failed. So the next story I will tell you toward the end of this talk. So let's continue with this first of all. Okay, this is what we did. So let's start with now the first part. Okay, but before that, let me again talk about very, very basic techniques that are used, because that's the beauty of this result, that they are using very simple techniques, but results are so magical. Okay, what is it actually? So this is graph given to you. Suppose we are given two subsets of vertices A and B. So what can we say about the capacity of the curve defined by A plus capacity of the curve defined by B and the intersection and union as well? Let's take some example in this case. Okay, so what can I say about it? Let's take some example in this case. A is like this. Suppose A and B are disjoint. Then how will it look like that incident on A and B? Like this. And of course, these edges also. And you can see very easily that, look, these edges don't contribute to the right hand side. So what is the inequality in this case? It is the following. This is when they are disjoint. When they are overlapping, let's see in that case, these edges, A minus B and B minus A, they won't contribute to the right hand side. So it always holds in fact. This looks like a very simple inequality, yes, it's very simple also, but it has major consequences, very major consequences. What are they actually? If A as well as B define ST min cuts, then A union B and A intersection B also define ST min cuts. Really interesting. Let's go further. If A as well as B define global min cuts, then the union intersection also define global min cuts, provided A union B and A intersection B are also global cuts. They define global cuts. Also, terminal cuts also, as long as A union B and intersection B are standard cuts. So this is really, I would say, this is very major consequence that this simple inequality is having. Okay, fine. So this is last terminology I am going to use, parallel cuts. So this is one cut, this is another cut. So two cuts, as you could see, parallel in the sense that if one of them is sort of another offset actually. In this case, shown in this case, they are parallel actually, they are not crossing. Is this only possibility? No. It's quite possible that they are like this actually. They are crossing actually. So basically the thing is that they partition vertices into four disjoint subsets, like this in this case. In this case we call them crossing cuts. So a pair of cuts can be either parallel or crossing. It's quite easy for you to see. Okay, this all they are going to use in today's talk. Okay, so this also largely cactus graph in this case. So cactus, let me just remind you this picture actually. This is what cactus actually is, and this is will help you to define definition also in this case for this what it is. An undirected graph is said to be cactus graph if each edge belongs to at most one cycle. At most one cycle. Okay. So of course a tree is a degenerate case of cactus graph, but interestingly, cactus can be represented as a tree also without loss of any functionality. So we can have a tree data structure that captures the entire functionality of cactus graph. Yeah. So they are in fact equivalent if I look at storage in this case. Okay. So that, some question please. At most one cycle.
Oh.
At most.
Sure, at most one cycle. So then the C and the cycle is itself cycle and vertices is a cactus graph, right?
Yes, so we can still implement it as a tree. So that's actually like to talk about it, but it's a very dependent thing. We can even take this graph as a tree data structure, which has all the functionalities of it. It's very standard, actually, we can discuss. Okay. Let us start with part 1, very light, but again we are focused right now on undirected multigraph. Okay, complex structure for ST min cuts. So this result is from 1980s. So first let's ask simple question. How many ST min cuts can there be in a graph? Okay? Because you want to store them compactly, which is a very good question to ask in this case. So a very simple example in this case, let me say n nodes are here. Here is source, here is sink, and this is what I do. Okay? So how many min cuts are there? So let's see, let me ask a simple question. Can you spot a min cut? Yes, very easy. This is one min cut. This is another min cut. Are there other min cuts also? Yes. Take this vertex. This is also a min cut. Okay. In fact, consider any sort of vertices. In this case, keep them on side of S, remaining side of T. This is also a ST min cut. So how many ST min cuts are there? Exponential. In this case, 2 to the power n. So we cannot afford to store them explicitly. Right? So this again raises the question, can you store them compactly? Fine. Okay, so let's take some example in this case. Let's look at this graph. Tell me the value of ST min cut. What is ST min cut value in this case? 3? 2? Why 2? Because these are like multipliers, you count them 2x. So 3x, right? You could see 3. Okay, capital ST min cut is 3 here. Let me give some example also. So let's say, suppose x is set of all ST min cuts in the graph. This is one ST min cut. I'm going very slowly so that all of you are with me. This is also ST min cut, and this is also ST min cut. This is also ST min cut. There are many ST min cuts are there. Let me ask a question right now to all of you. Is there ST min cut that separates u and v in this graph? Is it? Likewise, if there is a min cut that separates x and y also. You can convince yourself it is not. So what we can do is, every pair of vertices which can be separated by an ST min cut, just compress them. And this gives us a quotient graph. Quotient graph defined by all the ST min cuts. Let me denote it by Gx. Gx is quotient graph defined by G. It looks like any ordinary graph, right? Undirected graph, multigraph. But Picard-Curran showed that this has a very elegant structure lying there. So I take a break of half a minute, think about it. What is it? This is an undirected multigraph. It has very rich structure. Okay, so let me show you what it is. It is a single source, single sink, balanced stack. Because how can it be? It's an undirected graph. But we say the following: we can assign direction to the edges in this graph in a unique manner. Direction is unique only. So the resulting graph is single source, single sink, balanced stack. Quite long term. Let me define to you what it is. Single source, single sink, balanced stack. DAG is directed acyclic graph in this case. So a directed acyclic graph is said to be, this family in this case, is one vertex with 0 in degree. This source vertex. And it will be one vertex with 0 odd degree. Sink. So the single source, single sink is clear. What else? Now comes most important part, balanced stack. So SMT are called terminals. That every vertex is called non-terminal. Okay. So this is the thing. For every vertex V, this is called a non-terminal. What must happen when it's balanced? It has same set of incoming edges as the outgoing edge. Number if you look at it. This one. In degree V, same as out degree V. And so you could say that's what it is. So we can assign direction to the edge. Again, it's unique only. Okay, so let me show, for example, this is Gx. We can assign direction to the edges so that it becomes single source, single sink, balanced stack. Okay, you say how to do it actually. It is a simple exercise based on topological ordering. You despite the fact that the graph is like has balanced, every vertex is balanced in this case. Okay, you can transform this Gx into single source, single sink balanced stack in just order m time. It ensures that each assigned get a unique direction also. Okay, so this is what I'm showing this particular case like this. Okay, so if you look at any non-terminal here x, it has certain edges, but this transformation basically, if you look at it, it splits all the edges incident on x into two sets. I'm showing the color also in this case. S is green and T is purple. This is what I'm going to show in this case. So edges, some are green, some are purple, and same in number. What are these? These edges are lying on the path from S to X. These lying on the path from X to Y. And this is unique actually. You can compute in order m time also that way. So in fact, that's what it is. You don't have to store it explicitly. It's already there actually. Okay, so this due to this structure, I will call it as a. So this is, let me say, this is going to be unique orientation of Ex, orientation basically this way, and we call it as a inherent partition of Ex. So what it say the following, that every non-terminal has a unique inherent partition of Ex that gives us this text. It's going to be unique only. And we are going to call it as a strip from now onwards. So remember it, we'll use it later on. This is what it is. Any questions here about this strip? Yes, please.
Sorry, what is the rotation Ex?
What is?
E of x?
Ex is a set of edges instead of x. Set of edges instead of x.
Okay.
That's what it is. Any more question that you have? Okay, so let me know. Okay, this is fine, but what it is? You get a nice graph, whatever it is, but what is the consequence of that? And let me tell the consequence in this case. So let me ask you for this question in this case. Do you see this picture? Like for example, this is a ST min cut. You already know what the underlying graph are there, right? That's not introduced only, but do you see it is ST min cut? So again, let me say this. I have said that's in there, but you can ignore Alex. That's in this case if you want. Okay. So this is it ST min cut in this case? Yes, as you could see in this case. Okay, so so this is main theorem actually. So let me talk about it. Is this ST min cut? No, you could see that. Look at one thing to notice in the following. This case is that there are all basically edges usually living in this case, right? All edges are living out of this bubble which I'm showing this case. Okay, so if you look at this one, it's no ST min cut. But what happened in this case is the following case, that there is an edge which enters this bubble, and that's make the whole difference. So let me look at this theorem which is there actually. We say the following to look at it. A defines ST min cut if and only if. Now see this, if and only if. So let's say complete reference is given in this case. If and only if you look at this, this case Px, there is no edge in the strip that enters A. So this gives complete characterization of all the ST min cuts. You can check very easily whether a ST cut is ST min cut or not in this way. And this leads to many elegant data structures that answer various queries in a much more efficient manner. Kirti also mentioned a few of them, so that's what it is.
So this is true even with odd degree vertices in the graph, or I mean you mentioned it's even degree vertices.
It will be like, since the graph is undirected, to turn out to be the case that it will always have even degree vertices. It always have. They are always part of cross-quotient graph in that will come back.
Are we also interested in like compute how fast we can compute the question graph, or we are just?
Yes, so here again actually this is not something unusual. Let me say in this case what requires the following in fact. Look at it, let me see in this case. So you see in this case A defines ST min cut if and only if there is no edge in strip that enters A. Does it remind us something about Maxwell min cut theorem? Then how do you define a cut to be min cut? A cut is min cut if and only if in the residual network there is no edge which is leaving that. So that's the key in this case. So here again you can get this graph also in just single max flow from S to T. After that what you do? You compress SCC of the residual network into single vertex and reverse direction. So it is just there. You can get in just single max flow already there. Okay. Let's come to now the second part, which is more exciting in fact. Compact structure for global min cuts. Let's see this. Okay, so let me take some example in this case to start with. Suppose there are n nodes. Okay, global min cut cardinality. Let's say in this case, suppose this is the graph given to you, simple spanning tree. How many global min cuts are there? Every edge defines global min cuts. There are n minus 1. Okay, let's look at the other extreme in this case. It's cycle. How many min cuts are there? N choose value. What is the graph? Is complete graph. How many min cuts are there? Global min cuts. N, and how will you represent that? Okay. And so let's to get but inside, let's look at some simple graph which is quite generic enough to see what it is. Let's look at it. Okay. So again, even if you couldn't follow first part, it's fine. You can wake up now and focus on second part. It's totally different then. Okay, this is the graph given to you. Let's look at what is the value of the capital global min cut. You can answer this question. Think simple, 6. Okay. Let's try to support them. Okay, let's try to support them. This is one global min cut. 6. You can just verify it. I'm helping you in this case. 6. Okay. It has global min cut? No, it's not global min cut. Exactly. Are there others also? Let's try to do it. Okay. It's also global min cut. But count actually 6, 8, 6 only, whatever. Okay. Any more? There are many more. In fact, like this. Are others also more? Right? Yes. Like this. Very messy, right? Very messy, very messy. So just take a pause here and see that. Look, if you are seeing this problem for the first time, you'll say there's no way to go. It looks that how will you do it in fact. But there is a brilliant idea here, which was used by Garzanov, Lomonosov and Dinitz. And that is that, look, if you look at all these cuts, there is a very nice classification of all these cuts. Okay, let me help you here. Okay, look at all these cuts, for example, let's see this case. Let me help you, let's look at these cuts here. I am putting the vertices in the background. Okay, these blue are the cuts there. Okay, look at this cut, set defined that way. There's cut that crosses it, right? Fine. What about this cut? Is there any cut that crosses it? Or if you not put definite crossing there? Clear? Let me again show you here. There is no cut, no global min cut in this case that crosses this cut. Clear? Fine. So then what we do is, let's try to support all such cuts which are not crossed by any other cut. Okay? So every cut is going to be parallel to it. Fine. This is what picture comes. You can see also, and get convinced also, this is it. These are called laminar cuts in the community mathematics. Okay? So these are in this case laminar cuts. What are the cuts? They are crossing cuts. Let me show in this case. Some question?
Yes.
Yes, please.
On the previous slide, this green vertical cut is crossed by the diagonal cut, right?
No, let's go back. Let's see.
Like they all share those top two edges.
No, let's see in this case. A cut is defined in a set of vertices, unique manner. So this is, I'm talking about, for example, this in this case. Look at every cut is parallel to it. Look at the set of defined there. So don't say these are going to cut line actually. You have to look at the set of vertices there. So they are not. For example, if you go beyond this, it's not going to be like this. On the left hand side of it, all the vertices are there. For this, these are going to be these two vertices. This is proper subset of this in this case. Right? So again, look at definition of crossing and parallel there. Don't just look at line crossing. No, that will be very wrong if you do that. Okay?
I thought it was defined as like sharing an edge.
No. I defined that. If you look at that, there are 4 reasons defined by those known entity. Okay, so these are basically, you could say, laminar cuts, and remaining ones, if you see that, what are they actually? Let me bring them also here. So let's first have a look at it. Since these are laminar cuts actually, let's do one problem at a time. Can we store all the laminar cuts? So let me, I am showing this case, as you could see. I want to have a compact structure for storing all these laminar cuts. Okay, so remain fully focused right now. This is very important point of this talk right now. So let's try to see, can we have a structure that stores all the laminar cuts in a compact manner? And yes, if you look at it, I am helping in this case. Let me make this curve complete in this case, whatever. Okay, so what you see in this case, if you look at all these cuts, they have partitioned the underlying plane into various regions, right? You see that, look, each region is defined by a set of laminar cuts. For example, in this case, let's say that this internal region defined by this one only. What about this in this case? This region by this, and this. The region defined between lying the circle and running to also like, right? Clear? There are some regions which are empty also. For example, look at this region is not empty because it has this vertex, but this is not totally empty. You know what is lying there. So here is a simple way actually. What we could do is, we can have a tree in fact. For each region, what you do is you introduce a node. How to connect nodes? You connect two nodes if they share a cut. For example, in this case, as you could see here, this region and this region, they share this cut, so add an LP. Like this. Clear? So we get a simple tree structure that stores all the laminar cuts, all the global min cuts. As a homework, you can also try to show that if there are a pair of vertices which are separated by global min cut, then there is going to be laminar cut that separates them. Always going to be. It's always going to be. You can think about it offline. So this takes care of all the laminar cuts, and they're also going to be ordered only that way. Now come the main challenge in this case. What about the remaining cuts? The red cuts, which are crossing cuts here. Let's see this. Okay, they are still left for us. Clear? But if you look at it carefully, the laminar cuts, they must respect all these crossing cuts. They must respect the laminar cuts because they are not going to cross them. So not only laminar cuts have partitioned the plane into regions, all these crossing cuts are also confined within various regions now. All of them in various regions. Okay? Let me show in this case, for example, the crossing cuts in fact. Okay? Let me show you, for example, this pair of crossing cuts. This is lying in this region, right? You are keeping an empty node there, recall that. Maybe it's coincidence. Not coincidence. This is it. Likewise, if you look at the other one, let me show in this case. This again is lying in the region defined by these laminar cuts 1, 2, 3, 4, 5. Right? So we have all the crossing cuts partitioned into various regions. And yes, it's not coincidence. These regions must be empty. You can prove it using the homework I gave just now that every pair of vertices which are separated by global min cut, there is laminar cut that separates them. So these regions must be empty actually. Clear? It's fine, but not every empty region must have crossing cut there. So how to go ahead with that? So let me show in this case. For example, let's say we look at various regions, empty region in fact, if there is any crossing min cut there. Suppose in this case, what it is, let us see there are maybe other crossing min cuts also there. There has to be at least one more crossing min cut here, because otherwise this won't crossing cut at all. Let's draw that. And what happens in this case, we get now 4 cuts. And thanks to submultiplicity of cuts, there are also going to be global min cuts. Okay? So we get additional new cuts. Like from this case, we could get this cut. Is it crossing cut? Yes, still crossing cut in this case, not laminar cut. What do? Repeat same task. So what you get is that if a region has at least one crossing min cut, all possible cuts defined in this way are going to be Goldman cuts in that case, like all of them. Is clear to you that? So now how do you represent all these crossing min cuts? Again, I take a pause of half a minute. Again, think simple. It's a very simple data structure. It's already there in front of you. Just see this. There are these empty nodes. And what I've shown in this case, look, this is empty node in this case. Look at it in the tree in this case. Every possible cut in this case, crossing cut is a Goldman cut.
Is it a dual of the tree that you had?
No, don't require that also. Think simple. Think simple in fact. Okay, let me help you in this case. We already had this. In this case, remember that these empties were there. Let's look at this tree also, which we already had. What to do with the following one? Just look at this. Just blow these empty nodes and introduce this again empty nodes here. Can you see where are all the crossing cuts now? Here. Here again, how many? Again 5. So all the crossing min cuts are also present in this empty node. What is it? It looks something familiar? No, it's simpler than cactus in fact. Because if you look at it carefully here, no vertex is shared by more than one cycle. It's in strongest condition there. But why, where are the laminar cuts there? Although crossing min cuts are defined uniquely in this manner, laminar cuts are by multiple. For example, in this case, look at this laminar cut, and this both define same because this is empty node here. But this is what it is. Okay? So this is in fact a special case of cactus. I call this as a every vertex belongs to at most one cycle. It also implies that look average belong to at most one cycle. It's called simply as a T cactus. T for tree actually. Because I got it from by blowing up some empty nodes into the cycle. Okay?
So,
Yes, please. Some question.
why would every cut be a crossing cut? Is that
No, it's possible that there are no crossing min cuts at all. But there always have to be laminar global min cuts.
no, sorry. Is the claim that any in the cycle, any cut that splits the cycle
Yes.
is a cross, is a min cut?
Yes. Which I should.
It also has to split more than to one vertex, right? Because if it splits just one vertex,
Yeah, that will be laminar only. For example, let's
There
say
will be laminar.
this is laminar, but any such like which are defined by pair of non-different edges, it's going to be crossing min cut. For example, I could see if I look at this cut, then this is crossing min cut. Okay, so this is it. Let us see now basically. So commutations for global min cuts is in front of all of you here. So if you look at X set of global min cuts, then if you look at the GX which are there, the nodes of GX are lying these non-empty nodes only. Other empty nodes only. Okay, this is done by Konstantin Lomonosov more than 50 years ago, almost 50 years ago. And this is what they said actually. Just look at the elegant way they have generalized, they have expressed global min cuts. A cut in these global min cut, if and only if it is defined by either these green edges, tree edges, or a pair of edges in a cycle. You can call it as a minimal cut that way. Okay? How to build it? Cargan Parigari showed it 2009 only that it takes order m polygon time, and Saranok and collaborators show it takes only polygon maths also recently. So this structure, I think it's so elegant. I think we should know it. Okay, so now come to the main questions. Yeah, please.
So in the previous thing, why is that better than this? Is that how many polys are there in the log?
But this is different. First of all, this is Monte Carlo. It requires that. That is, yeah. So, and secondly, again, referring to max flow actually. But if someday we have order m time algorithm, then maybe this polar algorithm will be also smaller than that. A different way. For example, I should cut queries that way, so we can express just one max flow it requires. Now come the main question. Just see it. That's what it is. That's the reason in this case. See in this case, but I've seen this case is if S is 2, S is n, we have the answer to them. But it is a strip which is a DAG, special DAG in fact. If it is has m n, if S is n in this case, it is cactus of size order n. Let's see this. see it. These are two extremes, S2 and S equal to n here. Now come the main question, just see it. What structure for S greater than 2 and less than n? Why it is challenging question? It is challenging because the two extremes are totally different. There is a drag here, there is a tree there. Again take a pause here to see that look, how will it look like? You say it's going to be a hybrid of tree and strip or balance drag, but it is easy to say this, but how will it look like? Like that captures all this functionality, it captures all the main cuts also there. How will it do it actually? In fact, size order m only. That's the really the biggest surprise in this case. Or just order m in this case. Okay, so again let me just start with what is
No dependence on S. So size of S was what?
no, it don't depend on
So,
yes.
order M. If
Yes.
there is dependence on S, like
No, no. We'll see that also why. For example, here also like it's like yeah, we'll see that it's not. Yes, please.
So size of S is fixed. Like will you have different structure for different sizes of S?
No, it's going to be like in the degenerate case it becomes like this, not this there. So it's going to be a hybrid of cactus and something more. That's what it makes it so challenging. How will it look like actually? Okay, so let me just let's start with this third part in this case. Again by stroke 94 here. Okay, so in this case let me take some channel vertices like this actually. So again golden vertices are channel vertices and blue vertices are the no channel vertices. You could say that. Okay, and assume graph G is also a quotient graph, that is to make things simpler only. Okay, so this is it in front of you as you could see. So we want to have a structure that completely represents all the standard mean cuts here. They can be exponential as you could see. Okay, so now what is the starting point in this case? It's already known to them, to Dennis Feinstein earlier also, before this also. It was quite well known that way. It was the following. Look, each standard mean cut is going to keep some vertices, standard vertices one side, other remaining other side. Okay, fine. So each standard mean cut defines a partition of the underlying standard set. But not every standard partition might have a standard mean cut, right? So we say a standard partition is a valid cut if there exists at least one standard mean cut that defines that. Okay, so in this case, say, so this was starting point in this case. These are called non-terminal in this case, whatever. This was the main point that they say that this was already known to them, that if you look at only this valid cut of S, we can have vectors for them. So like this, let me show you. Here is the graph, and here is a vector structure that stores all the valid cuts of S. Is it clear to what is valid cut in this case? I explained to you that there must exist at least one standard mean cut that defines that. But it is inadequate, as you could see here, very inadequate, because it is totally silent about how are the remaining non-terminals blue vertices appear there. Totally silent. It is totally not good at all. Clear? Any questions here at this place? Please let me know. Any question?
So all the edges are also required. Like if you remove some edge, then some cut will be not present. Then all these green edges are required to preserve.
These edges, if you look at these edges, are the structural edges. They are not in the graph actually.
No, what I'm saying is there a smaller representation graph which can also preserve all the cuts?
No, it's
this is really the
and reason why do they say it? Because actually if you look at this like global milk cuts or the standard milk cut in that way, they define a crossing family of cuts, and as a result by Dennis and someone else, that every crossing family can be represented by a cactus there. So this result was already known to them, but it is inadequate, as you could see. We need something more, because we now want to know how this will look like. How will this disappear? Okay, so this is a starting point in this case. So let me just say in this case, so this is called T cactus there. Okay, storing all valid S cuts. Okay, so let's see in this case, for example, I am drawing here a standard mean cut. Okay, again it's value still the 6 on in this case, standard mean cut, because 6 capacity here and this is S plus some line inside. Can you see which cut represented there in that case? S1 S2 on one side, remaining other side. Can you see that? It is. So there could be, in fact, I'm showing two standard min cuts, but they both belong to this valid S cut. Clear? So multiple standard min cuts represented by same valid cut of S. Okay, let me give you some more example in this case, just to make you familiar with this. Look at this in this case. S9, SA. This again 6 in this case, standard min cut. 2 standard min cut. Represented by that is going to be this cut. So there are many standard min cuts printed by single cut of this one. Okay. So can you think of, right now don't aim for order M, can you think of a compact structure, some structure that stores all the standard min cuts with the help of this detectors and whatever you know till now?
Sorry, I have a question.
Yes, please.
Maybe this is obvious, but is the reason you can do this is explicitly because each of the vertices in the standard set is a leaf in that structure, is it not?
It's not necessarily leaf. It is coincidence here too. It's not leaf node. It's not leaf.
Okay.
Not necessarily. Internal node could have standard vertices there. It is because global min cuts as well as standard min cuts, they define crossing family, and there is a result which shows that we can have a characters that represents all of them, all those cuts.
If you have only k standard nodes, then I think 2 to the power k nodes are always sufficient to like preserve a structure. I mean,
That's but we want the generic one. You can't assume that specific. So things, yes, please.
Will you replace green edges with dags?
Excellent. That's what it is. Every cut basically. Every cut. Look at every valid cut here. How many cuts can there be? How many valid cuts will there be? At not S square, right? At not S square, because this is a character structure there. Every cut is either a 3S or a pair of Huygens cycle at not S square. So for every valid cut here, excellent. What you do is the following: you build a strip there. So this also let me show in this case. For this cut, I build this strip actually. What strip? I will keep S1, S2 on one side, remaining all on the other side. I build it. Can you see that this will store all the standard min cuts corresponding to S1, S2 on one side, remaining on the other side? Yes, that's what it is. Clear? But let me ask you here, how will define this vertices? Yes, it's quite simple in this case, S1, S2 on one side, and S3, S2, S9 on the other side. Okay? Other example here, let me this in this case. S4, S5, S6 one side, remaining other side. Like this. But this is about the standard vertices. What about the non-terminals there? How will they appear in this strip? Let's say for example here is a non-terminal. Here, where it will appear in this strip actually? What are possibilities there? Quite simple, it has three possibilities. Either it basically become part of source here. It become part of source here if there is no standard min cut that separates S1, S4 on one side and this other side. Or it could become sink also. Okay, in this case, there is no standard min cut that separates this unit from these actually. Another possibility, yes, it is that it becomes a non-terminal in this strip also. Clear? Fine, it's there. But what is the problem with this approach here? We have S square valid cuts. Each strip require order M space. So it becomes, so this is that, sorry, one thing I want to say in this case. Whenever it happens that it is become a non-terminal here, I call it as basically that this non-terminal is determined by the valid cut. Distinguished by valid cut. It's becoming a part of the whatever this diagram. Okay. So the problem with this approach is that it takes MS square. MS square. Our aim is order M only. Yes, please.
Could you just explain the previous case? So, we'll just go on. So, if there is a cut that has S4, S5, W
Yes.
as a rest, so if you place it in the middle, how does it account for all cuts?
No, okay, let me see this. So it's, let me go back here. So this is one non-terminal here, right? Okay. What can happen is that, look, there is standard min cut. Okay, but there is no standard min cut that keeps S4, S5, S6 on one side and omega on the other side.
Okay.
Then it's going to be, in this case here. Likewise here. Otherwise, it is going to be distinguished here. It shows there is a standard min cut that keeps S4, S5 on one side, this on the other side, likewise this also. Okay? But you can MS square space only, which is huge actually in this case. Our aim is order M only. Yes, please.
So can the same vertex be in multiple
That's the next question that's going to happen. So we have, so this, you can see this is not going to lead us to order m immediately here, but what should we do now, right now? Let's explore all the strips, and he's giving the right question in this case, that maybe all these strips are not totally different. Maybe they are not totally different there. And this is the main insight that will be used. Let me show you, for example, in this case, actually, let's see. Okay. For this, actually, if you look at this strip here, let's see in this case what is strips? S1, S2, S3 on one side. In this case, S1, S2, S3 on one side. Right? And in this case, let's pick in this case here. Let's say this is one channel min cut, 6 here. And let us focus on this omega 1, omega 2 here. Clear? So this is you, right now you see a standard min cut that keeps omega 1, omega 2 inside of source here. Okay? But there is also standard min cut that keeps omega 1, omega 2 inside of sink also. So where will they appear? They will appear inside it. Is it possible that both of them get glued together? And the answer is impossible. Why? Because I can show you in this picture here a standard min cut that separates omega 1, omega 2 also, and here it is. And since a strip stores all these min cuts there, it must be separated. This is a very key point that look, in each strip, if a non-standard unit is distinguished there, it is going to appear as a distinct terminal, terminal like this. This is going to appear there. Clear? Omega 1 like this, and omega 2 like this actually. So this is one of those in this case, as we said, distinctness of omega 1 is preserved in a strip that distinguishes it. It remains as it is, not joined with other vertices, other. Second one, which is even more surprising in fact, okay, this is, in this case I am showing here this cut here, distinguishes omega here. Let's look at this cut in this case. Again look at omega 1 here. You can see here again, the strip for this is going to distinguish omega 1. Right? Now the question arises here, how will omega 1 appear here? Will its inner partition change? And the answer is no at all. It will appear as it is. Its inner partition is there, will be identical here as well as here. And in every strip that distinguishes it. This shows that there is a huge amount of similarity among these, all the strips that distinguish a non-standard terminal. The starting point here. Now the question is, this is the main question, this I am just going to get there. Yes, yes. Okay, I just need 5 more minutes because I started quite late, 5 minutes late.
We have 5 Take all the time.
Okay, so this was these were nice insights, but still it doesn't tell you the real magic there. What are aim in this case? Let's see this. For each non-term in this case blue vertex, we want to have a compact representation of all those valid cuts that distinguish it. They can be quite large. And what they showed is the following result. So this is, I just mentioned the others in this case, they are identical. These are two starting inside there, but after that they will leave the great work here that we show in this case. What is show the following? Look at omega 1 here. We can represent all those valid cuts that distinguish omega 1 by a path in this cactus. And this path is not ordinary path, I will tell you. This is omega 1 is like here. There is a path here in cactus that compactly captures all the valid cuts. But how do you do it actually? Let me show you in this case all the valid cuts there. This valid cut distinguishes omega 1, fine. What about this actually? It is part of cycle here. Okay? Every valid cut defined by whose one edge is this one. So like these three. They will distinguish omega 1. Next one is again easy. Next one, in this case, gets a fine. But it's fine, but the path could be quite long in fact. Notice that this path is not ordinary path. Every cycle it passes through, it shares exactly one edge. It's a proper path. And due to this reason, you don't have to store it explicitly. Just storing the endpoints here is adequate. You can retrieve this path easily. So we require just order one space to capture all the valid cuts that distinguish a non-terminal in this case. So this is, I'll call it as a, basically this is called a Pearson mapping in this case. Pearson mapping. That every non-terminal haze is mapped to a path, proper path there in this case. It can order one space. And this structure divide them. What they do the following. A quotient graph induced by phenomenon cuts, they call it as flash graph. Vector storing all valid cuts, they call it as skeleton. And last but not least, this most important point here, mapping what is of f to pass in x is called Pearson mapping. So flash, skeleton and Pearson mapping there. Space, order m, order n, order n. Together, so this is called the Monte Carlo class in this case. How to show that this is really powerful? This solves the entire problem. Let me tell you here by this example here that we can represent, we can compute the strip for any valid S cut in this case in just order m time. For example, this is the what I've seen in this case are these channel vertices here, and these are these no channel vertices. I'm showing them in gray color in this case. What you know about them is they are going to be like this. This is omega 1 by omega in this case, omega 2, omega 3, omega 4, and sometime it can also happen that it is mapped to an empty node also. It's also possible. Let us look at now, let's look at this question, how to report a strip associated with a calculation. For example, like in this case, this one. Let's see this. This shows the real power of this entire structure which is there. How do we do it in this case? Something is quite easy. In this case, we know what are the vertices standards lying on one side of that. S1 lying on one side, remaining all on one side. Right? This is going to happen very easily in this case. But now comes the main question here, how do we take care of it? Which of them are going to appear in source or sink or distributed by the strip in this case? Okay? Omega 1. Omega 1, if you look at it, pi omega 1 shares an edge with this cut. We defined by these two edges. So this is going to be distinguished here. Omega 2. Omega 2 is totally lying on the one side of that. So which side it will lie? It will lie into the sink side there. Omega 3 in this case. Again on one side, over there. Omega 4. Again shares an edge with it. It lies. And likewise omega 5. And since I told earlier also, we can get the entire strip once we have this one in just order m time. That's the power of this structure. It is so compact, but it still preserves all the independent also all these standard methods. Okay, they total together called it in this case order m structure in this case, but now come the story in this case. They gave this result in 1994 here, but majority of these theorems were without proof. No, because it's reason also because there were phase limits were there at that time there, and then they gave a general version in 2000. Detailed analysis of for the case when channel cut value is odd only. But when it is odd, actually, this skeleton happens to be a tree structure, which is much simpler actually. And they also wrote the following actually. Detailed analysis of the general case, even case actually, will appear somewhere else. Okay, so firstly I must say that look, a personality like Dinitz actually, they knew about it, but they just, due to some reason they didn't write it up, maybe due to it. But they of course were absolutely correct there, they didn't give the details. So I and my student had hard time trying to find the proof, because they are not at all there, they are partly given there only. So this is, the main changes are the following in fact in this case. Number of valid S cuts may grow from order S to S square when it is even case. Another challenge also, multiple minimal cuts in skeleton that represents same valid cut. There are really challenges there when you go from odd value to even value. Okay, so this is what we could do in this case. Both odd and even case, myself, my student, this year they printed in society. Both odd and even case. Let me give a slight evaluation of that. First part is complete proofs. Complete and self-contained. Including from the strip also we define it and practice also. Second part, simpler and alternate approach. This is, I would say, the major most significant contribution in this case. Why? Let me tell you in this case. In this paper actually, they introduced locally orientable graphs to explain the results, which is a generalization of directed graph. It's quite complex. Very complex. That's why we couldn't put it. Second part, they prove some three-star lemma. Very intricate proof. Very intricate proof it was. What we do is the following. All proofs, they use simulative cuts or some very elementary graph properties. That's it. And last but not least, our analysis doesn't have any distinction between odd and even case. You know, some even case only, it's for all of them. But I must say here, really genuinely in this case, we have since gratitude toward Dennis and Weinstein that they arrived at this result. And I now feel that why this result didn't get wide publicity, because it was very tersely written paper actually. Okay, what we have done is we have just made it more accessible actually. We feel that in 3 years we have worked hard on it, making simpler and simpler. I think now it is level where you can teach it in a class also. But again, praise goes to Dennis and Weinstein for this great work. Okay, last part in this case, open problems. Algorithm for graduated carcass, how to build it actually. We can build in order S max flows, we show it also that way. But can we improve it to order 4 log S max flows? This question, main part of volume is skeleton and person mapping actually. Skeleton, yes, we can do it. They have been shown examples follow from the work of Sandrak and collaborators. We can do it in polylogarithmic S max flows. This is the main thing. Okay, so with this I conclude. Yeah. Any questions if you have, just let me know. I'll share.